Yes, sir. Yes, sir. Ready, sir. Hello. 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 Voice is there. Hello. Hello. Hello.
Hello. I request Professor M.K. Kokila, Professor, Department of Physics, Bengaluru University, to chair this session for 6 papers. Like what I have already mentioned, it is OP1, OP2, OP4, OP7, OP8 and OP9. These 6 students will present their oral presentations. And before we go for the presentations, Madam Kokila did her bachelor's degree in 1983 from National College, Basungudi, the other campus of this management only. And then MSc from Central College, that is Bengaluru University. PhD degree again from Bengaluru University only. She has done on X-ray crystallography and other related things. And she has experience about some 30 years, almost from 1986 to this. And she has published about 72 papers in national and international reputed journals. And she has attended nearly 60 national and international conferences, and recipient of Dr. Kalpana Chawla Young Women Scientist Award. Let us give her a big applause. And she has already guided more than 10 students for their PhD program. And now we have requested her to chair this session. I request Professor Kokila to chair the first session, OP, rather for 6 members. Madam, to you.
Good afternoon, everybody. Now let us start the oral presentation. I just call should I mention?
I mean, time here. Yeah, okay. Time is 8 minutes presentation, 2 minutes question and answer. The question can be asked by the audience and ultimately by the judges and even the chairperson also. Anybody can ask, but anyway, your presentation is only for 8 minutes and questions for 2 minutes. So, you can start. Madam will start now.
Oral presentation 1, title of the topic on the studies of bell-like states by Rohit Rn. That is, these are the authors: Rohit Rn, Charles S, Balakrishnan. So, who is presenting now?
Rohit. Rohit.
Rohit Rn will be delivering this talk. Thank you. I welcome Rohit.
A very good afternoon to one and all. Am I audible, sir?
Yes, yes.
Okay. I'm very delighted to present our work. We had a set conference in our college, during which we did the work on the studies of bell-like states under the guidance of Dr. Balakrishnan. I am Rohit, along with my colleague Charles, and I will be presenting this in the IAPT National Students Symposium. So, beginning with, as Dr. Professor Deshmukh has enlightened us what the quantum world is, what is quantum physics, but in very brief and very small notes I would like to say, Gordon Moore stated a law that power of computation will double every year with a constant cost. Now you can see at the very beginning there was a computer as big as a room, and now it has reduced like you are using in your palms the mobile phone or the laptops. So what is happening really is when we are reducing the size of our computers, classical computers, our instruments are getting smaller and smaller. Now from micrometer, nanometer, we have now reached to nano chips and very several designs. So what we are trying to do in a very small space, we are trying to inculcate many components. Because of that, when we will exceed this limit, we will enter into the atomic dimensions, that is 10 to the power minus 10 or Armstrong units. At that time, the quantum effects will come into picture, and we will be not able to achieve what we do in classical computers. So these are the shortcomings of classical computation, and very fundamentally to tell, quantum computation is based on the phenomena based on laws of quantum physics developed by many quantum physicists around the world like Einstein and many others. So as in classical computation, we work on a very basic principle, that is switch on and switch off, what we call as bits like 0 and 1. Similarly in quantum, it is not we cannot compare it, but I can tell as an analogy. In quantum computation, we deal with quantum states known as 0 states or 1 state. It is represented by the vectors like ket and bra vectors. So it is similar to like spin up is 1 state and spin down is 0. So we in quantum computation, we use these two very important principles, and these are represented in the form of matrix. So our work is related to something like that, and as sir has mentioned, quantum computation has huge amount of applications in quantum teleportation, quantum dense coding, quantum communication, and quantum cryptography, and many others, and which are being used and utilized all over the world, and it is being very famous in our transactions, whatever. It will provide a huge amount of security to your devices, your communication process, everything. So getting into our work, at the very beginning I would like to introduce some key concepts which we have used in our project. So the first one is entanglement. Actually we have two types of states. One is pure state and one is a mixed state. In pure state we deal with something called as single qubits, and in mixed states we deal with something called as multipartite systems. Many qubits are there. The concept of entanglement, as our professor had described, entanglement is something like if we have two electrons and we know the state of one electron, we can, if we say first electron is in up state, we can immediately predict or instantaneously tell that other electron must be in the down state. But it is not as simple as that. We need to work on much of complex mathematics, and there are many things. In very classic example, or I had read one article in that it was given, a very classic example was if we have two twin brothers, and suppose one thinks of a song in his mind and the other begins to repeat that song orally, then there is some communication between them two. It is not very related, but we can you can understand this example very clearly. So, as I mentioned, there are two types of states, pure states and mixed states. In pure states, we have two types. One is the product state, one is the entangled state. If we cannot represent a state in this form, that is psi is equal to tensor product of two vectors, then we call it as an entangled state. Similarly, in mixed state, we have a product state and a entangled state. If we can't represent the density matrix of that state in this product form, then we call it as an entangled state in a mixed form. Now, coming to the next part, for what we up till now know, we know maximally entangled Bell states, which are also known as EPR pairs or EPR states. So these states have been extensively used, and they have these are available in many references. They make use of these states to formulate the concepts like quantum teleportation. These have been explained by using these states. So but the problem in Bell states is that it is very difficult to maintain these states, because we know if we have an electron, by Heisenberg uncertainty principle itself tells that we can't measure its position and momentum at an instant. So if we are trying to measure the state of electron, its state will obviously collapse, because we will be giving some energy to that electron. So it is very difficult to maintain these maximally entangled states. So what we did was we tried to go to the very generalized state known as Bell-like state. Here we can see the parameter A, which is called as degree of entanglement. Obviously it varies from -1 to +1, but in our calculations we have considered it as positive values. From this state we can see, if we substitute A is equals to 1, we get the first Bell state, equation number 3. So this similarly we can have other Bell states using this A values. So now coming to the next, the three parameters what we have used to study in our project is, first one is amplitude damping noise model. So in any communication system, even if we consider our classical communication, previously there used to be very much noise or distortions. You might have seen the previous televisions, you could see some dark black and white spots coming on your screen. So that are due to various reasons, like there will be a noise, there will be an effect of another signal, or the communication channel might not be good. So similarly in quantum computation we deal with different noise models like amplitude damping, squeeze damping, or generalized amplitude damping, and phase damping and all that. But here in our project, specifically due to lack of time and all, we just considered one parameter, that was amplitude damping noise model, in which we can see n is a factor called as noise, degree of noise. It varies from 0 to 1, and these are the Krauss operators. We took it from the very famous paper by Dr. Anirban Pathak, and we have used this extensively in our project. Second is von Neumann entropy. We need to classify, or we need to know what state is the given state. So like it is a mixed state or a pure state. From pure state we can obtain very good information very easily, and from mixed state it's really difficult. So what does von Neumann entropy tells us? If von Neumann entropy is 0, we come to know it is a pure state, and if von Neumann entropy is 1, we come to know it is a mixed state. The third parameter is the fidelity. Fidelity tells about the distance measure of how much a state is deviated when it is transported to some other person. So it is just a measure to know how much your signal is not affected or affected by any communication channel. Now we have did this project in point of view of the communication, So coming to the objectives, our first objective was to calculate von Neumann entropy for Bell-like states. Second is to calculate fidelity for Bell-like state, and third is to achieve correspondence between von Neumann entropy and fidelity. So beginning with, due to lack of time, I will just proceed with the calculations. So the first one is we calculated von Neumann entropy for bell-like states. We have bell-like state given by this operator or quantum state, and it can be represented in density matrix by the outer product of the psi vector. Then we get this relation in form of Dirac notation, and we need to take out partial trace. Now what we have considered is, if there are two persons communicating, suppose Alice and Bob, Alice is communicating to the Bob, then she is sending her bit to Bob. So only her qubit is going to get affected. Obviously there are other possibilities that Bob's state might also get affected and Alice's state also might get affected, but we have considered only one way. Oh, sorry. Only Alice qubit is getting affected. So we came to a relation, von Neumann entropy is related to degree of entanglement and noise, and varying these two parameters we get a pure state. Then we plotted the graphs in relation to them, and we got very nice values for what is the correspondence between von Neumann entropy, noise and the degree of entanglement. Similarly, we calculated fidelity for bell-like state, and we came with equation in which fidelity is dependent on the degree of entanglement. Then we tried to, as our third objective was to calculate, to achieve a correspondence between them. So we again we plotted the graphs, and by mathematically von Neumann entropy is dependent on, is a logarithmic function, while fidelity is a linear function with respect to that. So we cannot achieve a mathematical connection, but we try to do it using mathematics and we, graphically, and we got these intersection points. So let me tabulate this. We have tabulated in the form, and we can observe that minimum noise and minimum degree of entanglement, we get some correspondence between, or intersection point between von Neumann entropy and fidelity. So coming to conclusions, first one is von Neumann entropy increases with the increase in degree of entanglement, and it decreases with the increase in degree of noise. And similarly for von Neumann entropy is 0, as we mentioned, like for pure state and mixed state. Fidelity decreases with increase in degree of entanglement for given degree of noise and vice versa. And I will directly come to the last conclusion which I want to emphasize on. So from this last conclusion, what I want to tell is, in any communication there would be obviously be noise, but we like to ensure the security of any communication channel. So in quantum communication channel, what if anyone third party is trying to steal that information, then what will happen is, if Alice and Bob are communicating, then the fidelity will go to 0. But how will we define whether fidelity is 0 due to noise or due to some interceptor? According to our equation, fidelity has some finite dependence on degree of entanglement. It is not exactly 0 in any case. So as per our conclusion, we can understand this by fidelity is not 0 due to noise. It is 0 due to some intercept. Thank you.
Thanks for the nice information, and he has tried to explain this whole phenomenon in a very short duration, and it is open for discussion now.
How do you define degree of entanglement? Can you explain? Degree of entanglement, how do you define that?
It was in one of the paper that
How do you define?
okay, the entanglement can be in various forms. Degree of entanglement. Directly I cannot explain, I will have to.
Then given a state,
Yes.
how do you determine whether it's entangled or not?
We cannot write in the product form.
No, that is the result. But supposing I give you a state,
Okay, sir.
is there a way of testing whether it is entangled state or not?
Yes, sir. There are
How-
different methods: partial positive transpose, negative partial transpose.
One explain that.
distillation.
Explain one method.
So, we haven't studied very exactly, but partial positive transposes, we have to take one qubit transpose, and then we have to find the
Why?
trace
I'm not
of.
talking qubit is not here. Just entangled state is given to you, quantum state.
Okay, the
Can you
quantum state,
say it is entangled or not? Okay.
it's very.
Now, please tell us, how do you say the two electrons are entangled? Supposing there is a beam of electrons coming out from a filament, heated filament, will all the electrons be entangled, or how do you assess that some given two electrons are entangled or not?
So it's Actually, practically I cannot tell, but what we worked was mathematics, and from mathematics there are different methods like partial positive transpose and distillation processes, so we can control the entanglement or distill out the to take out the information. But theory practically I don't have any idea.
Only one. Yeah, time is very short.
Yeah, the linear entropy you are talking is it is an what in our classical word we use in thermodynamics what we use, and it is similar. Actually, it's an analogy. What we did was it is an analogous phenomena that we study in quantum computation. So here entropy we try to express it is in completely a mathematical form from which we understand whether the state is pure or it is a mixed state.
Thank you. Thank you, Rohit.
Thank you.
Now, let us move to the second oral presentation on quark gluon plasma and its thermodynamic properties by Vibhor Khanna. He is from Indian Institute of Science Education and Research, Thiruvananthapuram. Am I right? Be quick.
Hello. Good afternoon, everyone. I hope I am audible. So this is Vibhor Khanna, and yes. So this is my research dissertation, which I did in the final year of my BSc under the guidance of Dr. Agam K. Jha. So basically, it was a 6-month project, but I gave 6 months extra. That is, I started studying it in the 5th semester. So it concerns about the quark gluon plasma, the QGP state of matter, which is known to be formed just after the Big Bang. After 20 microseconds, just after the Big Bang, everything is known to be in QGP state of matter. So yes, so this is my plan of presentation. First of all, I would give a general introduction about this standard model. So standard model is a formalism which tends to describe the 4 fundamental forces of nature and how they are mediated. So you can see there are these 6 quarks, 6 leptons, 4 intermediate exchange particles, and the 1 Higgs boson particle. So my dissertation work actually had the use of this up and down quark and strange quark and the gluon particle, which is the intermediate exchange particle for the strong forces. Okay, so these are the up down quarks, which are basically from the first generation, and strange quark, which is in the second generation. Due to the lack of time, I won't be getting deep into their explanation. So yes, so my the experimental work of my dissertation could only be done at RIC, which is Relativistic Heavy Ion Collider, and it is at Brookhaven National Laboratory, New York. So it is one of its own kind. Apart from this, we have SIR, the LHC, Large Hadron Collider. So most of the work was theoretical and computational. So moving forward, so first of all, the general introduction about the QGP state of matter. So when when the particles of the baryonic medium are in the free state, basically the protons and quarks, which we say, are further made up of quarks, and they are binded by the strong interaction, and which is mediated by the gluon particle. So when these are freed of their strong attraction, then we have this QGP state of matter, which is actually liquid like, unlike what scientists thought in the first, that it would be in a gaseous state. So it is formed at very high temperatures. To give you an idea, it is like 10,000 times more hot than the core of the sun. So my guide, that is Dr. Agam K. Jha, he formulated, he actually worked on a statistical formalism to analyze this state of matter, which was in the journal of his papers, and the name of the paper was Simple Statistical Model for Analysis of Quark Gluon Plasma Droplet, and we also we also say it the fireball for the obvious reason because it is too hot. And my work was based on his paper, the potential which he, the expressions of the potential coupling constant he has formalized. I further calculated the energy of one droplet of the QGP state and plotted with respect to the radius. So first of all, I made the already done work, I reproduced it, and then I took the mass of the gluon and quark particles dependent on some parameters. So why is it important to study this QGP state of matter? Basically what I said, that just after the Big Bang, the whole universe was in this QGP soup state of matter. And if we want to realize that how the universe expanded, or what were the parameters which resulted in present day, so we have to study this state of matter. So now I will be briefly talking about the quantities and expressions that are used in my dissertation. Okay. So as I talked about this, it is based on a simple statistical model for analysis of QGP droplet fireball, and my guide was had worked on this paper. So first of all, the phenomenological flow parameters, which is represented by the gamma, and it basically shows the dynamical flow nature of the QGP. And in my dissertation, I have taken this value as a constant to 1/6 for the quark particles, which is represented by the subscript Q, and for gluons, it is taken to be 6 times the Pfizer value of quarks. And the other parameter, that is the QCD parameter, represented by capital lambda, is taken to be 150 mega electron volts. Now the other one is the QCD coupling constant, whose expression is showcased here, and the main use of this QCD coupling constant or defining is so that we can further get the expression for the potential, the confining potential of the QGP droplet, and for the actually there had to be this expression. I don't know why it is not there. The PPT I sent, it was there, but basically there is a big expression for this confining thermal potential, and this was chosen by my sir specifically for defining or the analysis of QGP. And for the density of states, for defining the density of states, they use a Thomas Fermi model to define it, and basically by using these expressions we have done the computational work. So for the energy of so they actually I don't know why the PPT I sent to the people for presenting here, it had all the expressions. Basically to carry forward here, here was also the expression for the free energy of quark gluon plasma, and similarly the QGP droplet is like surrounded by a pionic medium. Pions are basically type of particles, and it stabilizes the droplet. So there was also the expression of the pionic medium, and similarly for the free energy of the interface, which is the Weyl interface we say. And finally we had the total energy of the QCD droplet, which was the summation of the free energy by quarks, by gluons, by the Weyl medium, and by the pionic medium. And actually there it was the expression of the mass of quark and gluon which I have taken, which was kind of some new work problem which I solved, unlike my professor, my guide, who took the value of quarks and gluons to be 0 in this case, but I took it dependent on some other values and recreated the work, that is the plot of energy versus the radius. So this was when the mass of the quarks and gluon is taken to be 0, we get this type of curve, and here there should be the curve which I have created. I don't know how it will come here. So yeah, thank you. Finally this was my presentation. This was Vibhor Khanna. Now I am open for questions. And first of all, really sorry because some of the expressions were missing. I am really sorry about that.
Mr. Khanna, can you please tell me what is that you have studied, that is thermodynamic properties
Yes.
of these?
Yeah, so basically whenever we talk about studying any state of matter, the most basic thing we are interested to know is about its free energy. And now here the work of thermodynamics comes. That is, I have deeply studied about the different type of potentials during my dissertation work, but it was all which was in our course, and also about the standard model. And this free energy, the plot of the free energy which is made, it is actually where the thermodynamics part comes.
You should have listed that in your presentation. That is important, no?
Yes.
Main thing. Okay. It is open for discussion.
Yes, now questions please. Sir, it was basically at BSc level in the final semester of BSc. Sir, currently I am in MSc, but I did this work in my BSc last semester. I am first year MSc. Yes, sir. Yes, sir. I did my BSc from Kirodi Mal College, Delhi University.
Wonderful. Now, is it a combination of gluons and quarks separately? Because our concept is something like gluons are inside the quarks. But now you are separating them out. Is it a mixture of gluons and quarks?
Yes, sir. Basically,
They appear separately.
yes, sir. They appear separately. Sir, let me tell you. The theory which defines the strong interactions is the QCD, quantum chromodynamics, in which the intermediate exchange particles, that is the gluon, also takes part in the interaction, unlike the QED theory, that is the quantum electrodynamics, in which the photon does not take
I
part.
got one more question.
Yes.
Density of states.
Yes,
What
sir.
is the shape of the curve? Density of states. You plot a graph of density versus the energy, no?
Sir, actually the graph is for the energy versus the radius of the droplet.
Okay, okay.
And
Okay, now I understand.
Yes.
Thank you.
yes, sir. Yes, yes. Yes.
Whatever the equation which you use for potential,
Yes, yes.
because any of those equation is not appeared,
Yes, sir.
whether it is for Newtonian fluid or non-Newtonian fluid.
Yes, actually, the thing is that we do not have enough experimental data so that we can give any assumption or any statement that this QGP was a Newtonian or a non-Newtonian fluid. But there is one point that we can choose any confining potential, but specifically that one potential was chosen which could be fit into the computational work, and that was done by my guide, and that is kind of like where after that part my work starts. But it was basically the confining potential which confines the whole state of matter and makes it stable to exist.
Now people they will use the Rayleigh-Jeans potential and so
Yes.
many types. No,
Yes,
that is
yes,
because even that is not appeared in your slide. That
Yes,
is what
I'm
I-
really sorry about that. Like I told them that I want to use my laptop only to showcase.
You could have done.
Yes.
Okay, thank you.
Any questions from student side? Yes.
Yeah, we can.
Yeah, in your
One-
last plot that didn't show up
Yes.
because that was your result. Can
Yes,
you
sir.
at least like give a sense
Huh,
of how
yeah,
it looked?
Yeah. So let me tell you what is it about. It is a very simple, like the exponentially increasing curve, which showcase us that with the increase in the radius, the energy is like increasing exponentially, not exact exponentially, which shows that when we take the mass of the quarks and gluons greater than 0, then the state of matter is highly unstable and which couldn't be existed. So basically this notion that quarks and gluons may have mass up to some mega electron volts or something like that is like not correct. We have to take it 0 or very small, very small. So as the work which was done by my professor, which showcases that after a point of radius, the energy becomes negative, and hence it proves that the state of matter was stable.
Thank you, Mr. Khanna.
So thank you everyone, and really sorry for some of the lag. Thank you so much.
Now, let us move to the oral presentation 4, that is on understanding polarization of light through experiments on the verification of Brewster's and Fresnel's law by Ajay Rohan, H, Department of Physics, Bengaluru City University, Bangalore. Now I welcome Ajay Rohan.
Hello. ಪೆನ್ನು ಅಪ್ಲೋಡ್ ಮಾಡಿದ್ದೆ ಅಜಯ್ ಆರ್ ಎಚ್ ಬಿ ಸಿ ಯು ನೋ ಅಜಯ್ ಆರ್ ಎಚ್ ಬಿ ಸಿ ಯು ದ ನೆಕ್ಸ್ಟ್ ಒನ್ ದಟ್ಸ್ ಅ ಪಿಕ್ಚರ್ where's the projector? The laser pointer. No, I was not given a laser pointer. Controls.
This is next.
Okay.
This is previous.
Pointer.
This one, mid one.
All right.
Hello. Good afternoon, everybody. I'm Ajay from Bangalore City University, and I'll be presenting on understanding the polarization of light through experiments done on the verification of Brewster's law and the Fresnel's law. But before that, I would like to thank Professor A.R. Usha Devi and Sarbari Bhattacharya, who provided the optical labs for me to perform this experiment, for us to perform this experiment. And I would also like to thank Shruti S. Iyengar, doctoral student and faculty at the Department of Physics, Bangalore University. So light is an electromagnetic wave, electric field and magnetic field oscillating both perpendicular to each other and perpendicular to the direction of propagation. What is represented here is the electric field vector and unpolarized light and polarized light. So defining polarization here, polarization refers to restricting or retaining the electric field vector to a particular plane. So unpolarized light has electric field vectors in all planes, and all of these electric field vectors are perpendicular to the propagation of the wave, whereas polarized light has the electric field vector restricted to just one plane. So the Brewster's angle, formulated and theorized by Sir David Brewster, the law deals with the polarization of light by reflection. Light is maximally polarized at the Brewster's angle being an angle of incidence. The polarization lies in a plane perpendicular to the plane of incidence. At the Brewster's angle, the reflected and refracted light are perpendicular to each other. Now this point is very important because it helps us to formulate the next equation through the Snell's law actually. So the refractive index of the interface formed by the two media is related to the Brewster's angle by tan theta b being the Brewster's angle, giving the ratio of the two media, refractive index of the two media. So the experimental setup consists of a source. We've used a sodium vapor lamp as a source, a condensing lens to focus the image, a collimator and a polarizer mounted onto the collimator. The prism is used to reflect light coming from the source, an analyzer mounted onto a telescope. The analyzer is just another polarizer which is mounted onto the telescope, and the image is viewed through the telescope. So what is extinction? Achieving minimum intensity of the reflected image is termed extinction. This series of images are taken for extinction at the Brewster's angle. So this is what extinction looks like, which is minimum intensity. Next slide. Okay. The plot of extinction angle versus the angle of incidence for different readings of the polarizer. So on first glance, we can see that all of the curves are sigmoids. So all of the curves are sigmoids and all of them have the same inflection point. The inflection point is the point where the curvature changes, the shape of the curve changes, and at the inflection point, the x coordinate gives the Brewster's angle, and the y coordinate gives the orientation of the plane of incidence. Now how do you know that this is the plane of incidence? It's because the polarizer angle, which is between 10 and 20, is a near straight line. So that corresponds to the plane of incidence. Also, another plot of extinction angle versus the polarizer angle for different values of angles of incidence shows a curve something like this, where the point where all the curves intersect, the the y coordinate gives the orientation of the plane of incidence, while the x coordinate gives the plane which is perpendicular to the plane of incidence where extinction happens. Also, it is to be noted that for the angle of incidence very close to the Brewster's angle or at the Brewster's angle, the curve has a slope of 0. So that is to be noted from this one. Next up, we have the Fresnel's law. The law relates the angles of incidence and refraction to the polarization of incident and reflected light, and is given by the equation tan theta is equal to minus tan alpha cos of I minus r by cos of I plus r. So it has the same experimental setup, but what we've noticed is at the Brewster's angle there seems to be this discontinuity in the curve or the straight line. Also, for angles very close to the Brewster's angle show large deviations from what should have been observed from the equations. So why this is happening is, setting alpha, which is the angle of polarization of incident light, to 45 degrees, we can show that tan theta divided by the ratio of the cosine terms to be equal to 1. Now if theta at the Brewster's angle is 90 degree, then tan theta blows up to infinity, which is what is seen here on the left side of the on the graph that is towards my left. So there is a discontinuity, and the two extreme points represent the angles which are very close to the Brewster's angle, which are skewing our results. So the slope actually turns out to be greater than 1 here, which is 1.2, and the slope here comes up to be 0.6, which is totally out of what is to be expected. But if we assume that the curve is continuous, and if we neglect those 2 points, extreme points which correspond to the angles close to the angle of Brewster's angle, then the curve is a straight line giving a slope of 1, which essentially verifies Fren's law. So conclusions. The verification of Brewster's law requires the use of single polarizer. Oh, I forgot to mention this. Yeah. For the angle of incidence close to the Brewster's angle or at the Brewster's angle, the curve is a straight line, which means whatever the value of the polarizer, extinction happens at the same angle, which means there is independency, which means the light can be crossed with the help of just one analyzer, which is seen here. Light was actually crossed using just one analyzer at the Brewster's angle. So conclusion. The verification of Brewster's law requires the use of a single polarizer mounted either on the collimator or the telescope at the Brewster's angle. The Brewster's angle is unique for interfaces formed by two media. The nature of the curves in the plot of extinction angle against angle of incidence for different polarizer values are sigmoidal. Now since they are sigmoidal, taking the differential of the sigmoidal would yield inverted Gaussian, where the maxima or the minima would give us the Brewster's angle. The differential of the curves yields a Gaussian, where maxima minima yields the Brewster's angle. The verification of Fresnel's law should be done for angles other than the Brewster's angle because the value of the slope blows up to infinity, and should be done with sensitive instruments for measurement for angles of incidence to be taken very close to the Brewster's angle. So from these conclusions, we were thinking, how do we take this forward? So what's next? We thought let's try and get refractive indices of liquids. So we started with a hollow prism, and that didn't work out because light was reflecting off the surface of the glass and was not the reflection from the glass and water interface. So we came up with this idea of a vertical spectroscope having just a single polarizer mounted onto the telescope. So the source is replaced by a laser, so there is no need of focusing it or using a condensing lens. Also, since the water cannot be rotated to get reflection, we thought of
time is up.
Yeah, I'll just wrap up. I thought of having symmetrically opening arms so that reflection can be viewed, which satisfy the criteria of reflection, where angle of incidence is angle of reflection. Telescope is replaced by the photodetector, and polarizer is mounted onto the photodetector. So one has to just open them up, view the extinction, and take the tan of that, and that would give the refractive index of the two interfaces. So that concludes my presentation.
What is the value of Brewster's angle?
For glass, the value was calculated to be 1.501.
Brewster's
Sorry,
angle.
for glass, the refractive index for 56.33 degree.
Okay. Are you studying there or working?
I'm actually from BCU. I'm in my final year, so we didn't have optics labs at BCU because the department was very new. So I was permitted by the chairman Usha ma'am to conduct the experiments.
Got it. Okay.
I'll be
There are
taking
any
questions.
questions from student side? Thank you.
Yes, yes, sir.
Okay, now,
Yes, sir.
are you an MSc student?
Yes, sir.
Okay.
Final year.
Fine. Why do you use prism for reflection?
Sir, any surface can be used actually.
Oh, you were
Any
using,
flat surface.
it so happened that you were using
Yeah,
prism.
yes.
Is there any preference that
No,
you
we
had
actually
in-
used, we've also done it with thin glass
Okay.
slides
Mhm.
with water in between them.
Okay,
So
okay.
we've observed thin film interference.
What are the different materials you used? Because you showed so many graphs, no?
Right now we've just done it with glass.
But
we-
so many curves you showed, no? It is for
those
different
are for
materials.
different angles of the polarizer, sir.
Okay, okay. This Fresnel's law.
Yes.
Which one came first? Is it Fresnel's law or Brewster's law?
So the Brewster's law, because the Brewster's law is
Okay.
quintessential for setting up the.
All right. Where do you actually use Fresnel's law?
So to know the
Yeah.
polarization of the reflected light.
Okay, okay, okay. Oh, is it 1 minute? This is a centuries old formula, no? This
Yes,
two?
yes, sir.
Oh, is it the people have not investigated these things earlier?
I've
No,
not
it is
seen-
just a
Yes.
clarification. Don't worry.
Yes, sir.
Can I ask Chairman? Now, in conclusion itself you have shown at the last end, that is the accuracy part. Accuracy part, I think you itself having a doubt, because you mentioned the sensitive instrument. That means what kind of, to avoid the, or to overcome this
Sensitivity.
error,
Sir, I think,
what you have taken care of?
Sir, I think
Because
using,
basically optics experiments itself is a sensitive experiment.
yes.
And also you mentioned that sensitive instrument, that means you have doubt that many errors will be committed.
I think what I'm referring to is since the polarizers are very small, we cannot actually set the polarizer to, that kind of angle.
No. Why I am putting this question
Yes.
is, this graph what you have shown,
Yeah.
because all points will meet at a one point. That is, to get that you use the equation, tangent equation, that sine theta by cos theta. If you use any tangent equation, you should be very careful and your resolution should be high, accuracy should be high, then only you have to use the tangent equation. That is what my comment.
Okay, sir. Yeah.
Thank you, Rohan. Now,
Thank you, everyone.
let us move on to next oral presentation, that is OP7 on synthesis and characterization of AGI, that is silver iodide ceramic solid state electrolyte by Anjali Verma, and Anjali Verma from School of Basic Sciences,
Infinity or
Department of Physics, CSJMU Kanpur. Welcome, Anjali.
There is a pointer. Good afternoon to all the dignitaries and research scholars present here. I am Anjali Verma, MSc Physics student at Chhatrapati Shahuji Maharaj University, Kanpur, Uttar Pradesh. First of all, I would like to thank to Padma Shri Professor H.C. Verma sir and M. Dinachandra sir for guiding me throughout my work. I would also express my gratitude toward the conveyors and organizers of this symposium. The title of my presentation is Synthesis and Characterization of Silver Iodide Ceramic Solid State Electrolytes. These are the outlines of my presentation. First of all, energy storage device. Why we need energy storage device? Due to heavy demand of energy, we need an energy storage device to store its energy for prolonged operation without any interruption. There are mainly two types of energy storage device, that is battery and capacitor. Batteries, we all are familiar with batteries. It is a very well known energy storage device which store energy in form of charge. We use battery in our daily life, as in our vehicles, in our gadgets, everywhere. Battery contains three parts: anode, cathode and electrolytes. Basically, we are working on electrolytes. Today, we are using a battery having liquid state electrolyte, but there are many disadvantages of it, because they are made of toxic aqueous solution that is not good as a safety issue, because their thermal stability is very low at high temperature. So at high temperature they may cause many fire accidents. For overcome this disadvantage, a new technology is developed that we call solid state electrolyte batteries. Solid state batteries have a potential to approach the potential of high energy density demand. As we can see in this graph, the energy density of lead acetate batteries is very low, that is approx 20 watt-hour per kg. But the energy density of lithium metal ion batteries is very high, that is approx 200 to 250 watt-hour per kilogram. There are many advantages of solid state electrolyte, that it is very high energy density at high voltage, and this is made of very non-flammable materials, so it is very good at safety issue. In our work, we are using silver iodide as an electrolyte, because it is the only well-known existing compound that has superionic behavior. This is the experimental procedure that we had done in our lab. First, we take the stoichiometric weight of AGI and its oxide fillers, and after that we pelletize it using hydraulic press. At 1000. After that, we pelletize in hydraulic press using 10 mm die bar at 1000 psi and 500 psi pressure. Then we obtain the cylindrical pellets. The cylindrical pellets are then obtained in the furnace for annealing. After annealing at 500 degree centigrade temperature for approx 14 hours, we measure the ionic conductivity of Y sample at 1 kHz frequency. These are the results of our work. It is a temperature dependent ionic conductivity graph of silver iodide, in which we can see that insert this, there is a temperature profile of our furnace which shows that the heating rate of our furnace is approx 5 degrees centigrade per minute, which also show that the ionic conductivity is gradually increases with temperature, and the ionic conductivity of our sample is 6 into 10 to the power minus 6 Simon per centimeter at 60 degree temperature. In graph B and C, when we made a pellet of 500 psi and 1000 psi pressure, their ionic conductivity, there is a difference in their ionic conductivity after annealing. But when we anneal this, before annealing, but when we anneal this, there is no difference in ionic conductivity of silver iodide at both pressure. This graph shows that the ionic conductivity is pressure independent. When we use the oxide fillers in our sample, there is a interesting result in this, that when we mix the 6% SiO2, that is purple line, and the ionic conductivity reduces at one order of magnitude. Similarly, when we mix the 4% of Al2O3, that is green line in graph F, the ionic conductivity of AgI is gradually increases. When we measure the temperature dependent ionic conductivity this is a comparison graph of ionic conductivity of AGI with SiO2 and Al2O3. In this graph, we can see that the activation energy of pure AGI is 0.52 eV, the activation energy of 6% SiO2 is 0.47 eV, and the activation energy of 6 Al2 is 0.43 electron eV. There is no difference between activation energy. We cannot fabricate battery in our lab, so we are trying to test this test the electrolyte by making it as a capacitor. For making it capacitor, we use a carbon as electrolyte. The carbon that we put in our sample is made in our lab by carbon paste that is made with 80% peanut carbon, 10% carbon black and 10% binder. After that, we coat this carbon paste on our sample that is that's to form a capacitor, and we measure the capacitance using capacitor meter. These are the results of these are the cyclic voltammetry curve for all solid state cells at AGI with our best configuration. The scan rate is 1 MV per second and the capacitance is 3.6 farad per gram. Thank you, and at last I acknowledge Shiksha Sopan for Science Research Explorer program.
I just wanted to know what is that you have prepared, what is that you have synthesized here?
Solid state electrolyte.
Where you can use it in different
batteries. Ma'am, actually we are using liquid aqueous state electrolytes, but we are trying to make it a solid state because there is many laws. Due to safety, they are not safe, and the thermal stability of solid state electrolyte is very high at high temperature.
Okay, thank you. Discussion. That is, it is open for discussion now.
Why did you select this material for electrolyte, and how is the performance with the capacitor, as a capacitor?
Sir, we select the AGI because it is the only existing compound that shows super ionic behavior.
Okay, so what is to do with that?
Sir, we can use it in a battery as a electrolyte. Its capacitance is very high. To enhance its capacitance, we use some oxide fillers with it.
Okay.
My question is not more interesting because nowadays people are trying for low cost battery.
Yes, sir.
I think this is the work. I think you go through the nature paper and materials letters. There are thousands of paper will get on this superionic and all these things.
Yes,
And many a power paper is also there. But what I am requesting you, go for low cost experiment. This is the trend. Instead of going for lithium, go for sodium battery.
No, sir, we are working on AGI.
No, they're just suggestion. Whether you can implement, that is different.
Okay, sir.
You can ask any people, that is a different story. Another thing is, I noticed there's some graphs. I think below some temperature, some conductivity showing. Whether is it, what type of polarization is there? Because you are not mentioned in any of your slides. That is important. Another slide I saw that some like a curve reaching from on and off.
Just
Whether
go
is
back
it
to
a
your-
switching behavior or not? That is what. If it is there, and work more on that. No, not that. IV characteristic. Last.
Last. Sir, actually we are working on it.
Yes.
It is not complete graph.
That is. If it
Yes,
is
sir.
there, that is a
It is
switching
not,
behavior. But
yes, sir.
moreover, your material is not having any chalcohalide or chalcogenide in that content. Very rare
Yes, sir.
to get that.
Sir, actually we are working on it.
No, you
project.
should not put there.
Yes.
Thank you, Anjali. next oral presentation will be on radiation pollution hunting in and around Bangalore and its consequences on living beings by Ashutosh Sriram from Department of Electronics and Communication Engineering. Huh? All four of, okay. One other will be Deepa Kulkarni, Aditya Ganesh Pai, Gauri M, MB and Revan Siddhappa. So how long you want to take?
From same. Part by part, yeah.
But time will be 10 minutes.
Yes, ma'am.
Okay? You just share among yourselves.
Ma'am, the
Yeah. 2 minutes each.
yeah, ma'am, ma'am, we probably need another mic because.
You can take this.
Yeah, that one.
So you are also PS in
Yes, ma'am. Is the mic working? No, we'll all be sharing the mic. I mean, we'll use that as well. No, for now, we're not using that. Okay.
Forward is backward.
Okay, and is this on?
Yeah.
I think it is.
Yeah, this is on. I will.
Sure. Wait, which is forward again?
This is not. This is forward. This is backward.
Okay.
This is forward.
Okay.
This is backward. This is laser.
Laser, sure. Yes. Good afternoon to one all present here. Today, we, the students of PES University EC Campus, Electronics and Communication Department, are here to present you the topic radiation pollution hunting in and around Bangalore and its consequences on living beings. My name is Ashutosh Sriram. So, in the 19th century, before the 19th century, majorly the sources of radiation were natural sources like the sun and other celestial bodies. In the 20th centuries, we had other artificial sources like radios, television communication, etc. But in the 21st century currently, we've had so many sources of radiation like mobile phones, laptops, etc., which is becoming dominant and starting to harm our environment. So, radiation pollution hunting, it is a process of identifying the amount of radiation at a particular region. We went radiation hunting around Bangalore to observe the increase in radiation and to find methods and ways to prevent it from harming living beings. Today we will be talking about our observation, the apparatus we used, and we will also be talking about causes of increase in radiation and methods of prevention. Our lives have become much easier with the advancement of technology, but this doesn't come without a price. Radiation pollution is not something that we can ignore, or else it will become a big problem in the future. So what is radiation? Radiation is an electromagnetic energy that originates from a source and travels in the speed of light. It has two forms, the wave form and the particulate form. Common sources of radiation are sun, kitchen appliances like microwave, and mobile applications like Wi-Fi, etc. The risk of radiation varies with its intensity. That is, at low dosages, it carries low risks, but at high dosages, radiation carries a high risk. Depending on the type of radiation, we can find different methods to prevent it from harming us. Radiation is of two types, ionizing and non-ionizing radiation. Ionizing radiation are the radiation which can remove an electron at the atomic level. This radiation can cause cellular imbalances and genetic mutations. Non-ionizing radiation, on the other hand, is a kind of radiation which, which causes heat. This can cause damage to our tissues. Detection and analysis of radiation can be done easily using a spectrum analyzer. With detailed analysis, we can find causes of increase in radiation and methods of prevention from radiation and harming us. Now, I will be passing on the mic to Gauri, who will be talking about spectrum analyzer. This one is forward, this one is back, this one is laser.
This one is forward. Good afternoon, everyone. What is a spectrum analyzer? It is a device which measures and displays signal amplitude which varies in frequency within its frequency range. It is used to measure noise distortion, which causes radiation pollution and is harmful for small birds and animals. Causes of the radiation pollution are using low-level non-ionizing radiation which is emitted by the mobile phones, which causes acute headaches and brain tumors. Leakage in nuclear power plant, which leads to DNA mutation in the people living around. Exposure to radiation even causes radiation fatigue, which is lack of energy and feeling tired. According to the graph here, nearer the residential distance to the cell phone base is higher is the health issues like fatigue, headaches, difficulty in concentration, memory loss, and so on. From the figure, we can see that using cell phone for 15 minutes has increased the temperature of the body. Prevention of the radiation pollution are using phones on the airplane mode when not calling, and using the conducting polymers like polyaniline, which is used to shield against the electromagnetic radiations, and using in the speaker mode to increase the distance between the head and the cell phone. Now my friend Deepa will explain about the project.
Hello. Good afternoon, everyone. Good afternoon, everyone. I'm Deepa Kulkarni. I'll be continuing the project. Motive of our project was to collect data on effects, causes, preventive measures, and radiation intensity of the EM pollution across places in Bangalore. Our project in large scale can lead to many advancements in many improvements in EM radiation pollution limits, preventive measures, and the overall health of the society. We wanted real-time radiation readings, so we used a real-time radiation spectrum analyzer. We found out that the radiation intensity depends on, we found out that the radiation in highly crowded places is very high. This is due to more number of devices, electronic devices, electricity lines present in the crowded regions. The picture here clearly represents the same. More the number of electronic devices, more is the radiation intensity. So why this project? Radiation emitted by humans. As we all know, humans have warm bodies. We emit infrared radiation of the wavelength 12 microns. Safer radiation levels for living beings, anything which is less than 6 gigahertz is considered to be safer for all the living beings. Anything which is in the range of 6 gigahertz to 300 gigahertz can lead to excessive burning and heating sensations. Where are we? The current radiation readings, the current radiation levels in the main areas of Bangalore, as our experiment show, is 2.5 gigahertz, which is a 47% increase in the level of radiation from last year, which was 1.7 gigahertz. Our students from PES University conducted an experiment last year, which conducted the same experiment last year and had gotten the results of 1.7 gigahertz. The EM pollution, the EM radiation pollution shows an exponential growth. It is expected to increase up to 11.69 gigahertz in the year 2025, which is a 587% increase in the radiation intensity from last year. We worked hard and collected readings across places in Bangalore. So here are the readings. IIM Bangalore. Now my friend Aditya will continue with the project.
Good afternoon, everyone. So it's basically a case study rather than saying a project. This is just the radiation pollution. The more intense the radiation is, the more the peak we have. So these are some places where more of the people are there and some less people are there. So small brief explanation I'll give. We all know what is WHO, World Health Organization. They have given us a average range of 900 megahertz to 1800 megahertz. According to our experiment, what we connected, we got an average of 980 megahertz. Compared to previous years, it has increased by 47%. But it doesn't mean that we should leave the concern saying that it's in the range. It is increasing gradually year by year. At some extent, it may cross the range also. So we have to give a concern that the range remains as constant. Rather than decreasing or increasing, let it be a constant so that nobody is affected. Now, current situation by the some other programs or other projects, they have come to a conclusion that they have seen sparrows getting at the stage of extinction because of these radiations. It's not that gadgets are emitting more radiations. It's more number of gadgets has increased than the radiation. The radiation emitted by the gadgets are in the limit, but the number of gadgets used have been increased. So the prevention have been mentioned before, and these are the previous year's readings. The previous year reading is missing here over here. These are this year's reading. We used a gadget called real-time spectrum analyzer, which showed us a real-time experiment. So conclusion is that development must be there, but it should be a sustainable development, so that everything is under control. If we won't give a sustainable development, there will be a great damage to human beings also. Thank you.
No problem. Thank you all. Now the talk is open for discussion. There is one question.
Hi. What do you think is the permanent or long-term solution for this? You guys explained the prevention. Do you see any solution for this? Because we are all very dependent on gadgets these days.
So as we said, if you have seen the slide in the prevention, we have mentioned small precautions we can take. The major precautions is the polyaniline thing, which can be used while the preparation of the small transistor, from the transistor to the gadget. We can use polyaniline, which will control the emission of radiation within the product and the emission of the radiation outside the product. And one more small measures will be using the phone at the aeroplane mode when not needed. Now when we are sitting over here, we are not using our data, but still our data will be on, which is of no use. At that time, we can just switch off the mobile data and put it on the airplane mode, so that the transistors, basically phones are made up of transistors. So those won't emit any radiations, and it may prevent to some extent, it may prevent the radiations coming out. So those are some minor things we should take care of. And the remaining things is the polyaniline thing. Those are the major one.
Yeah, to answer that question, we can even use conducting polymers to coat the transistor, like he said, which causes EMI shielding, which prevents harmful radiation from getting released from the device to your body, but rather it can accept radiation from outside to the device.
Is it cost effective?
No, not currently.
Hi, so there's been a recent study in areas in Karnataka where it's been found that about 63% of our drinking water has uranium content higher than toxicity levels allowed. Now, when there is higher uranium, we all know that there's cancer and everything. What I wanted to ask is, does the body become more radiation susceptible, and if that is so, how much more does it account for compared to what happens usually?
Like we had already given in the readings, as long as it doesn't cross the necessary threshold, it won't harm the body as of now. The reading, the threshold being from 900 megahertz to 1800 megahertz. and yeah, below 6 gigahertz.
Basically, our project is related to the non-ionizing radiation. The uranium thing is the ionizing radiations. So we are dealing with the non-ionizing radiation effects. So it is like it is damaging our DNA. It's like these are not causing our DNA like replication in DNA and all, but those ionizing radiations are affecting our replication in DNA. Those are ionizing. We are dealing with the non-ionizing radiations.
Yeah, I had a question. Okay, so my question was, in your talk throughout, you talked about intensities of radiation, but throughout the talk you have used gigahertz or megahertz or whatever, which are all units of frequency. How are you relating frequency to intensity? Because those two in any wave are unrelated.
So, duration of? So it's a real-time spectrum. It's a device which is based on the USB connection, and we use a software known as Signal VPU. And we have a device, real-time spectrum analyzer, prepared by Tektronix company. So that is based on our reading, like it's real-time spectrum. We connect it to the laptop and we run the software. We get the real-time radiations. It's current time. For ranges from 50 seconds to 60 seconds, like approximately 1 minute. So, like, pardon sir, but you're asking about the radiation, like the quantity that how much temperature will increase by the radiations. There is.
So that depends on the type of non-ionizing.
Mobile waves. If you keep a mobile very close to your head, these radiations they increase the temperature of the brain. I wanted to know the order of increase.
So, if with respect to temperature, if we speak, according to what we researched, there was a 3 to 5 degree Celsius rise in the temperature
Of the brain?
Like not like complete, like the surrounding, the temperature was increased about that much. Like we never experimented on that, but still we googled it.
But I saw from the diagram it was the temperature of the brain. From your slide, you had shown a brain, then you said temperature of the brain increases. Okay, leave it, don't worry.
Sorry, sir.
No, it's all right.
Thank you. So let us move on to the last presentation of this session on merging the merit of quantum mechanics and machine learning by Harsha Tejas. Only one person is present. Harsha Tejas by Jayanagar University, Bangalore. Welcome, Tejas.
I'll get my laptop. I don't know what the problem is. Maybe with the system. I'll get the HP. You need this one? Okay.
Thank you. Excuse me. Excuse me. It's not. Okay. Good afternoon, everyone. Am I audible? Yes. Yeah. Okay. Good afternoon, everyone. I'm Arsha Tejas from Jayanagar University with my co-author Raya Arika. Under the mentorship of Professor Deshmukh and Professor Jayavrinda ma'am, we chose the topic merits of merging quantum mechanics and machine learning. Why did we choose the topic? Because both the fields are helping each other develop. So, quantum mechanics is helping machine learning push its limits, and machine learning is helping quantum computers fix the problems. So, what is machine learning? As author Samuel stated, it gives the machine the ability to learn without explicitly programming. So, when it comes to a computer to solve a problem, we should explicitly give them the instruction how to solve a problem. But in machine learning, we just give the problem and the machine will learn how to solve the problem. So, machine learning is a branch of artificial intelligence, where artificial intelligence is we are giving the intelligence to a machine. And machine learning is where machine learns from the data through the time, and we have a branch deep learning in the machine learning, because machine learning has its limits. But when it comes to deep learning, we are trying to replicate how our brain works. So, we actually have a neural network where these nodes here replicate our neurons in our brain works. So, when we have a data, so we feed into through the model, and the model will try to learn the patterns in the data, and it gives the output, and we use something called back propagation to update the weights so that the model will learn better. And when we talk about machine learning, we have three types of machine learning algorithms. So, we have supervised machine learning, unsupervised machine learning, and reinforcement learning. So, what is supervised machine learning? So, when the machine has an idea about what the data is, so we use label data, then we call it a supervised learning. As the name suggests, it has a supervisor to teach what the data is. But when it comes to unsupervised learning, sometimes we have very large amount of data and we can't label all the data. So, what we do is we just pass in through the model and ask it to see what are the similar patterns and make it to cluster. And then when it comes to reinforcement learning, it's a reward based learning. So, we define an environment and an agent. So, if the agent performs an action that is in favorable of the outcome, we reward the agent, and if it's not in the favorable of the outcome, we remove a reward from the agent. Based on that, the machine learns. So we are actually focusing on how we can bring machine learning and quantum mechanics together. So all our devices that we use today works on binary bits. So it's either 1 or 0. But that's not how our nature works. That's how classical physics works. But the nature works like Richard Feynman mentioned, that if we could build a machine that could work like our nature works, then we could solve a lot of problems. So that's when quantum mechanics was coined, and when it comes to a binary bit, so it is like a switch. So it's either 1 or 0. But when it's a qubit, it's a superposition of 1 and 0. So it's not 1 and 0. It's both 1 and 0 at the same time. So what's the limitation of qubit? So we use a block sphere to represent the qubit, and the ideal temperature to store a qubit is close to absolute 0. Why do we need this temperature? Even a small change in the atom will affect the superposition, and it will come to the ground state. So that's the limit. That's like one challenge of storing a qubit. And as we add more, so qubits are really fascinating. How is it so fascinating? As we add more qubits to the computer, the power of the computer exponentially increases at a rate of 2 power n, which is not true with a classical computer. With a classical computer, for example, if you take 2 bits, and what it means by a qubit is, like I told, it's a superposition of 0 and 1. For example, if you take a 2-bit, in a binary 2-bit, we have 0, 0, 0, 1, 1, 0, and 1, 1. So which means so the possibilities are 4 possibilities, and a binary classical computer will tackle this each time. So first time it will tackle it 0, 0, 1, 0, 1, and that's how it solves it. But when it comes to a quantum computer, it actually solves all the 4 equations, all the 4 combinations at the same time. So that's how it increases the power exponentially. And we have George Bull here, who defined Boolean algebra, and Claude Shannon, who logically deployed all the Boolean algebra. And as all you guys know, Alan Turing was the first person to run a computer, and Richard Feynman in 1981 told that we could use a quantum computer to simulate quantum mechanics. And what is a quantum computer? What's the difference between quantum computer and a classical computer? For example, we can take a instance where we want to solve a maze. We want to go from starting position to the end position, and we want to find the shortest path. So how will a classical computer tackle this problem? Just like how you and I will tackle it. It will try to find all the possible, it will take all the possible ways and see which is the best way and figure out which is the best way. But when it comes to a quantum computer, it looks at all the possible combination at the same time. So that's how a quantum computer is so much more powerful than a classical computer. So it's a rapidly emerging technology, and it's so fascinating that we are able to access a quantum computer. Even recently, IBM gave us the access to a 64-bit quantum computer, which is really fascinating. And weather forecasting, for instance, weather forecasting, it has a lot of variables to take in. So a classical computer, at some point of time, it needs a lot of time to compute all the variables. So a quantum computer can solve that easily. And chemical reactions. So as you all know, all the chemical reactions happen on a quantum level. If you try to simulate that on a classical level, obviously it's going to come to a 0 or 1. But when we could do that on a quantum computer, that's going to open up so many possibilities. And quantum cryptography. So it is literally, they tell that it's not possible to hack a quantum cryptography algorithm. Why? If you want to hack a quantum cryptography algorithm, we're going to have to go against the laws of nature, which is not possible. And in 2019, Google claimed that they achieved quantum supremacy with their 53-bit quantum computer, which is amazing. So what is quantum supremacy? It solved a problem which a classical computer cannot solve. So they actually solved so the problem isn't really that important for, I mean, it's not really that useful for any of us, but then they just wanted to show that a quantum computer is more powerful than a classical computer. They actually solved a problem that could take 10,000 years for a classical computer to solve in just 3 minutes 20 seconds in a quantum computer. And we actually came across this amazing paper during our research, and so I'm just okay. When we all know the classical gates with or not, exclusive or and all the gates, but when it comes to a quantum computer, because of the superpositions, the gates are different. So here we have a NOT gate where it switches the gate. So when we have a 0 and we pass it through a X gate, it changes it to 1. And we have a Hadamard gate which gives us the superposition of the inputs. And what's more fascinating about Hadamard gate is when we give the superposition back to the Hadamard gate again, it gives us the initial states. And we have NOT gate. So NOT gate, we use it for a 2-bit. We can't, it doesn't work. It is designed for more than 1 bit. So we use it for a 2-bit. So in a control NOT gate, so the first bit is your control gate and the second bit is your target bit. So the control bit controls the target. So when the control bit is 1, then it performs a NOT operation on the target bit and it changes the state. So basically this actually looks like a exclusive OR gate. So actually Deutsch was stuck with a problem. He was actually wondering how is a quantum computer better than a classical computer. So when he was wondering that, he came across this problem where we have a black box and inputs. So basically this black box, we given a red and a blue ball, and we have outputs from the black box. So the objective was to determine what the function is, what the black box does. Does it have a constant or a balanced function? So what's a constant function? So the output is not dependent on the input. And what's a balanced function? When the output is dependent on the input. So here in this possibility, the red ball, the input is not dependent on the output, but here it is dependent on the output. So to solve this problem, it would take a minimum of 2 steps for a classical computer to solve this, but it would take just one step for a quantum computer to solve this. How is it possible? We use 2 Hadamard gates in the starting and 2 Hadamard gates after the function box. So like I told, Hadamard gates gives the superposition of the bits. So at the same time, it considers 0, 0, 1, 0, 0, 1, 1, 1. So this is how you can quantum computer can solve this in 1 step, but it would take 2 steps for a classical computer to solve this. So this is, and okay, so SVM is a very popularly known algorithm in machine learning, where it is used for both classification and regression. So we usually have two kinds of SVM: linear SVM and non-linear SVM. Where linear SVM, the data is when we plot the data on a graph, so we can draw a linear line that can differentiate between the data. So if we have a new point, maybe this is the new point. So then based on the graph, based on the line that was drawn by SVM, we can tell which class it belongs to. Now the laser pointer belongs to the red class, and if it's here, it belongs to the blue class. So that's how you create a equation that could classify the data. Just 2 minutes, I'm almost done.
Okay, finish it fast.
Last, just 2 minutes. And so what's the limitation of this is, sometimes we don't have a linear and non-linear data. So here if you want to draw a line that would classify between both the data, it's going to take a very complex equation, and which is not possible to do. So what we do is we try to plot this in a higher dimensionality, so we'll be able to draw a graph. So this is possible in a classical computer, but at one point, maybe so at maybe 3 or 4 dimensions, the classical computer will fail. It will just crash. So that's the limitation. So that's where quantum SVM kicks in. So it can increase, the dimensionality can increase, and it solves the problem. So here we can see the classes, it's not possible to draw a line that can classify these both data. So what we do is we plot it in a higher dimensionality graph, and here we can draw a linear line that can separate both the data. And this paper, quantum SVM was was deployed by these people. And here are some results of how a quantum SVM is better than a classical SVM. So we have a wonderful data called breast cancer by Wisconsin dataset. So that is a dataset where it classifies the data into, they take the images of a breast and they see whether if it has cancer or not. So when we run it against a classical SVM, it gives an accuracy of 85%. But when we run it against a quantum SVM, it gives an accuracy of 95%. So the margin of error is very low when we use a quantum SVM, and even the training time was super low compared to the classical SVM. So we can clearly see that quantum SVM is so many times better than classical SVM. And you can imagine machine learning is used everywhere. So at one point, machine learning is also limited because of the computational limitation. But we actually call a quantum mechanic as a natural parallel computer. So in a computer, so we have parallel processes running, but in a quantum computer, because we have different qubits running at the same time. So because of the superposition, we can call it a natural parallel machine. So I would like to point out that how fascinating it is that quantum computers, the more qubits we add, the computer becomes more powerful. So that pretty much covers it. Thank you.
Thank you. Now the talk is open for discussion.
In the case of classical computers, those gates, no, they actually are made up of this electronic circuits, NOR gate, NOT gate, whatever it might be, AND gate, all this. In the case of quantum computers also, what are the contents of those gates? How they are made of? Okay, okay. Okay, right.
Not the quantum nature. I think our Vice President is eager about the time. Now, you have shown 85% accuracy and 95%. What is the fun in going for the quantum? Only for 10%, no? Everything is a taking probability. And also you are using a parallel port and all these things. And if you are master in mathematics, you can use this higher level, no, density of function and Monte Carlo method. And to get the more accuracy, you can try it for that. If it is 85%, if you do the high level Monte Carlo method, you will reach nearly 88 or 90%. And not going for the comp.
Yeah, is there any question?
Yeah.
So I thank all the students or research scholars who have presented an informative, I think each and everyone except some which are not, I think as we heard about this batteries, AGI, so we have so many papers on such topics, no problem. So all are appreciated for their attempt made to present their work, what you had done. So wish you all good luck in future. Thank you.
Thank you, madam. Thank you very much for having troubled and staying back till now. So I request Shantala to, madam, please, Bunny. Oh, irli. Thank you.
Thank you.
Sir, ತಾವೆಲ್ಲ ಕಾಫಿಗೆ ಹೋಗ್ಬೋದು. ಇವ್ರಿಗೊಂದು ಸ್ವಲ್ಪ ಅನೌನ್ಸ್ಮೆಂಟ್ ಕೊಡ್ತೀನಿ. ಹಾಂ ಕಾಫಿ ಟೀ ರೆಡಿ ಇದೆ. ನೀವೇನಿಲ್ಲ, ನೀವು ಹೋಗ್ಬೋದು. ಹೋಗ್ಬೋದು ಈಗ. ಆಮೇಲೆ ಬೇಗ 10 ನಿಮಿಷದಲ್ಲಿ ಕಾಫಿ ಟೀ ತೊಗೊಂಡು ಬಂದುಬಿಡಿ. ಎಸ್.
ಇವತ್ತು ನಾಳೆ ನಾಡಿದ್ದು 3 ದಿವಸ. ಅವ್ರು ನಾಳೆ ನಿಮಗೆ ನಾಳೆ ಇರ್ಬೋದು. ನಿಮ್ದು ಇದಲ್ವ ಏನು ಓರಲ್ ಪ್ರೆಸೆಂಟೇಷನ್ಗೆ ಅದು ನಾಳೆ ಇರುತ್ತೆ. ಇವತ್ತಿದೆ ಪಿ ಜಿ ಅವ್ರದ್ದಿದೆ ಆ ಥರ ಇವತ್ತು ಇದೆ ನೋಡಿ ಚೆಕ್ ಮಾಡಿ ಯುವರ್ ಸೈಡ್ PDF okay fine okay cool next you send ncjaudi@gmail.com. ಈ ಹುಡುಗಿದ ಇವನು ಮಧುರ ಮೇಡಮ್ ಕರ್ಲಿಕ್ಕೆ ಹೇಳಿದ್ರು ಯುಕ್ತಿ ಮಧುರ ಮೇಡಮ್ಗೆ ಬರ್ಬೇಕಿದ್ರು ಮಿಸ್ ಕಾಲ್ ಕೊಡು ನಿಮ್ಮ ಪ್ರೆಸೆಂಟೇಷನ್ ಇದು ಮುಗಿಯುವಾಗ ಫಸ್ಟ್ ಮುಗಿಯುವಾಗ ಮಿಸ್ ಕಾಲ್ ಕೊಡಿ ನಿಮ್ದು ಆಗ್ಬೋದು ಅಲ್ಲಿಂದ ಅಲ್ಲಿ ಬಂತಂದು ಇಲ್ಲಿ ಏನು ಇಲ್ಲಿ ನೋಡಿ ಇದು ಕಂಟ್ರೋಲ್ ಎಲ್ಲಲ್ಲಿ ಇರುತ್ತೆ ನಿಮ್ದು ಆಲ್ರೆಡಿ ಆನಲ್ಲಿದೆ ಇದರಲ್ಲೇನು ನೆಕ್ಸ್ಟ್ ಕೊಡುವಾಗ ತೆಗೆದು ಗೊತ್ತಿಲ್ಲ ಇದು ಆಗಲ್ಲ ನೀವು ಇಲ್ಲೇ ನಿಂತ್ಕೊಂಡು ಇದರಲ್ಲಿ ಮಾತಾಡಬೇಕು ಇದೇ ನೆಕ್ಸ್ಟ್ ನೋಡ್ಕೊಂಡು ಯಾಕೆಂದರೆ ಓಡಾಡೋಕ್ಕಾಗಲ್ಲ ಅದು ಕೊಡುವ ಅದಾಗುವ ಏನಿಲ್ಲ ಏನಿಲ್ಲ ನೀವು ಫ್ರಾಕ್ಷನ್ ಮಾಡಬೇಡಿ ಯಾಕೆ ಗೊತ್ತಾ ಇದು PPT ಇದೆ ಅಲ್ವಾ PDF ಅಲ್ವಾ ಏನು ಕಂಟ್ರೋಲ್ ಅಲ್ಲ ಫಸ್ಟ್ ಪೇಜಲ್ಲಿ ಇರುತ್ತೆ ಹಿಂಗೆ ಇರುತ್ತೆ ನಾನು ಏನು ಮಾಡಲ್ಲ ನುಡಿಯಲ್ಲಿ ಇರುತ್ತೆ ಕಂಟ್ರೋಲ್ ಏನು ಮಾಡೋದು ಬೇಡ ಹಿಂಗೆ ಓಪನ್ ಇರುತ್ತೆ ನಾನು ಬರ್ತೀನಿ ಆ ಟೈಮ್ ಇಲ್ಲ ಬಂದಿಲ್ಲ ಇಲ್ಲ ನಾನು ಇವಾಗ ಮತ್ತೆ ರಿಫ್ರೆಶ್ ಮಾಡಿದ್ದೆ ಮೆಲ್ಲ ಅಮ್ಮ ಇಲ್ಲ 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 ಅನ್ಸೆಂಡ್ ಓಕೆ ಅದು ಇದರಲ್ಲಿದೆ ಡ್ರೈವಲ್ಲಿದೆ ಅಲ್ಲ ವಾಟ್ಸ್ ಯುವರ್ ಇಮೇಲ್ ID? ವಾಟ್ಸಪ್ ಅದು ಡ್ರೈವಲ್ಲಿದೆ ಡೋಂಟ್ ವಾಚ್ ಕೇಳಿದ ಇವು ಇಷ್ಟಕ್ಕೆ ಇಷ್ಟು ಮಾಡಿದೆ. BVJC ದಿ ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್, ದಿ ನ್ಯಾಷನಲ್ ಕಾಲೇಜ್. There's the channel name. What's your name? Sumaya. Just check it up. Sumaya. Just check it up. Sumaya. Well, this is not linked. Actually, it's in Drive, right? Google Drive. Where's video? You saved in laptop. Just send here and we will see laptop. Laptop. This is Google Drive, right? ಹೌದು, ವಿಡಿಯೋದಲ್ಲಿ ಲಿಂಕ್ ಹೈಪರ್ ಲಿಂಕ್ ಆಗ್ತಿಲ್ಲ. ಇದು ಡೌನ್ಲೋಡ್ಸಲ್ಲಿದೆ ಈ ವಿಡಿಯೋ. ಹೌದು, ಇದು ನಾನು ಅದಕ್ಕೆ ಹೇಳಿದ್ರಲ್ಲ, ಡ್ರೈವಲ್ಲಿ ಇದ್ದರೆ ಡ್ರೈವಿಂದ ಡೌನ್ಲೋಡ್ ಮಾಡ್ಕೋಬೇಕು ಅಂತೇಳಿ. ಇದು ಯಾರು ಕೃಷ್ಣ? ಹಾಂ, ಇದು ಬರುತ್ತೆ, ಇದು ಇದರಲ್ಲಿ ಬರುತ್ತೆ, ಆಲ್ಮೋಸ್ಟ್ ಬರುತ್ತೆ ಇದರಲ್ಲಿ. ಬಂದಿಲ್ಲ, ಫೈಲ್ ದೊಡ್ಡದಾಗಿರಲ್ಲ, ಲಿಂಕ್ ಆಫ್ ಆಗಿರ್ತಾಗ ಅವ್ರ ಲ್ಯಾಪ್ಟಾಪ್ ಲಿಂಕ್ ಮಾಡಿರ್ತಾರಲ್ಲ, ಅಲ್ಲೇ ಇರ್ತಾರೆ. Your laptop, we can connect your laptop and no tension ಮಾಡಬಾರ್ದು, don't worry. See, users Hanumakumar downloads DSMP4. ನಮ್ಮ ಹತ್ರ ಇಲ್ಲ, ಇಲ್ಲಿ ಬಂದರೆ ಇಲ್ಲಿ ಲಿಂಕ್ ಮಾಡೋಕ್ಕಾಗತ್ತೆ. ಇಟ್ಸ್ ಓಕೆ. Just leave your laptop, you can connect through laptop and connect ಆಗಿದೆಯಾ? Just wait, sir. 2 minutes, sir. One minute. You can present through yeah. Yeah. WhatsApp log out ಮಾಡಿದ್ರಾ? ಹಾಂ, ಮಾಡಿದೆ.
Good evening to all of you. Again, we are starting the oral presentation. And in this session, Professor M.S. Jogad is the chairperson of this oral presentation. In fact, when we requested him to be the chairman for this oral presentation, he has accepted. He has traveled from Kalaburgi, that is Gulbarga, about some 10-hour journey from Bangalore. All the way he has come, and therefore we have to give a good applause to him. And of course, his profile is very long. I will just tell you only in brief. And Professor M.S. Jogad, former Associate Professor of Physics and Coordinator, Department of Physics, KSWU Vijayapur, former Principal, SB College of Science, Kalaburgi, Karnataka, teaching experience 35 years, UG and PG, research experience 30 years, and awarded, that is most important item here, Sir C.V. Raman Karnataka State Award and Best Teacher Award by Students Evaluation. And he was Fulbright Award. With that, he had visited USA 1 year, and USA universities and South Korea, Hong Kong, and China for conference. Research papers, more than 50 papers of international and national journals. And like this, it goes on. I will request Dr. M.S. Jogad to chair the session. And in this session, we have OP10, OP11, OP12, and OP13. And in case if there is any student who is available from OP1 to OP6, if anybody has missed it in the morning, they can report it now. So right now, we start with OP10. And OP10 students are already available. Now I hand over the mic to Professor M.S. Jogad.
Yes. Give a big hand to Professor Nagaraj for taking this responsibility. Just 1 minute time I will take. This is started in the year something back in 99 and 2000. When I was with Professor S.D. Manti in Michigan State University. And he is a great theoretician, and also in that group, Nobel laureate also there. And Satpathy, he wrote a letter to the Professor S.D. Manti. Now I was in the same chamber, he asked about this. Now instead of doing some research work for teachers, we can have because many good students, they used to go to the USA and other countries. Therefore, to have one journal, and he suggested, Professor Manti suggested, and later we made a team, and Satpathy we made as a convener. One prize journal used to come. For the editor is only student. Only teacher has to just modify the research paper. That is how it started. Then regarding the conference in Punjab, he suggested, because during that period, we invited Professor Manti to the BRC, because I am the principal investigator of the one big project. And later we talked with Professor Sani, and at that time, many people like Satpathy and Satya Prakash, and even Professor Virk also. And with my request, Professor Wagnore also contributed. That is how started the Student Symposium at that place. Because I was the National Advisory Committee, 6 members they made the National, I am one of the National Advisory Committee for that, because I was student of Professor Manti. Now, in that what we have done, we have made a resolution. Every year we have to conduct Student Symposium fully funded by the IAPT. Then if any program goes in the north, they will fund fully. If it comes to the south, I don't know why these, because we are not putting pressure on them, or people here who are cooperating with bringing fund from KSCST and KST, I don't know. They are not given the full fund. That is one thing. Second thing is, the resolution is made, it should not be done. That I raised in the EC member and supported Nagaraju and later Venkatesh and even Kenneth also he wrote a letter. That is, it should not be in a one place. It has to move from one place to the another place. Later, Professor Nagaraj is taken seriously. And that how he got the Bengaluru last year in that college. What is that college? Indian Academy of College. The good thing he has done. Today you see here, this year, he took the same conference because he wrote a letter to the IAPT president. Oh, why you are asking this? That is our decision. Something started in email. Then I put a word. If you assign, for preparation we require. The later what is happened, many things later to that. Now this is how things are there. And one thing and what Professor Nagaraj, he kept the resolution also. He has not done in the same college. He moved from the another college. He obeyed the resolution also. Anyhow, for that, once again, it is not easy to hold this. Because conference, why you are doing this? Because to correct the research students, not for guide. Because you should cultivate the research ethics. That is the number one. And the data, you should not give others data. And also, without doing also, you should not present. That is the how student symposium we have started. If any mistake is there, experts are sitting here. They will ask questions, they will correct. That is one thing. Another thing, I saw that many slides also and also abstract. Being a physics student, I think here our Professor Samantha is there. Always he'll talk about the least count and significant figure. You see your abstract. Some students, they will write 0.02. I think judges, they know. Some students, they will write 0.0004 digit. I think being a physics student, you are doing the research work, you should follow minimum things, units and dimension, significant figures, errors, whether it is a random error, systematic error, whatever that is there. In that paper, you have to highlight. Without that, I think there is no difference between physics and chemistry people. But chemistry people also do the lot of things, what physics people will do. The difference is, we are very careful about the units and dimension. We are careful about the data. We are careful about the error. Earlier, our guide, morning he was there, Professor Krishnamurthy here, my guide. Even without putting the error bar, he would not accept. That once already told in Gulbarga also. Many paper, though we have done jointly, he's not put his name because I have not shown so many things. Now that is the days. Now I request all the research students, whether your guide misguided or that is a different story. Ultimately, you are the held responsible. You should write correct units. You whatever data you are done, you do that. Don't copy from others because nowadays plagiarism check is there. Even if you put within a fraction of second, that will show how many 80%, 90%, 98%. I'll request, above all, I'll request the purpose of the student symposium, what we brought in IAPT banner is to improve the quality of physics education and physics research. Thank you very much once again to the Nagaraju and Bengaluru team, Tolle, for giving an opportunity. I will request you start that. Post number 10, oral number 10.
Good evening, one and all. This is Neha Sagar Algapalli from St. Piuston Degree and PG College from Hyderabad. Today we are going to present our research work, that is the comparative studies of ultrasonic wave parameters in organic liquids using acoustical grating method. So first of all, let us know what is an ultrasonic wave. So generally humans' audible range is from 20 Hz to 20 kilohertz. So above 20 kilohertz, the range, the frequencies of sounds is called as ultrasonics. Ultra means beyond. Sonics means sound. So beyond sound, beyond the human's audible sound, it is called as ultrasonics. So here there are two methods for producing ultrasonic sounds. That is the magnetostriction method and the piezoelectric method. Here in our work, we are using the piezoelectric method. So why we are so fascinating, like why to use these ultrasonics, why to study about these ultrasonics is, now today in the development of this ultrasonic technology and the advancement of the ultrasonic equipments, here the physical and chemical effects of the ultrasonic waves are used in research hotspots. So there are many in day-to-day life there are many applications. So here are few applications. I am going to explain few of the applications. The first one is the bat echolocation. That is, bats generally produce ultrasonic waves. The incident wave goes and touches the obstacle and then the wave reflects back. When the distance between this incident wave and the reflected wave, it calculates and it can pinpoint its obstacle or its prey. So the same principle is used by sonar, where sonar, the ultrasonic waves are produced and the sound, with the frequencies of the sound, it targets the target ships, and it can also see the obstacles like seabeds and everything. In submarines it is used to target the ships. The next one is the ultrasonic imaging. In ultrasonic imaging, what happens is, generally the ultrasonic waves are produced in the machine and they are penetrated into the skin, and those bounces off the baby and form an electronic image. This electronic image is converted into an echo, and the echo produces the image. That is the concept of ultrasonic imaging. And the next one is the deer whistles. Deer whistles is an instrument which is kept on the vehicle. When the vehicle is in motion, the air passes through it and it produces ultrasonic waves so that to alarm the deers. And the next one, last one is finding defects in metal blocks. If the metal has any defects, the ultrasonic wave doesn't pass through it, it reflects back. If it doesn't have any defects in it, so that the ultrasonic waves pass through it. The next is the objective of the work. Over to Samaya. Thank you.
The aim of our experiment is to do the comparative studies of ultrasonic wave parameters in various organic liquids using the acoustical grating method. Among various methods, we have chosen D/Sears method since it's very simple, precise and rapid. And also it's available in our physical laboratory. So this is also one of the reasons why we have chosen to do research in this area. Let us talk about the construction and working of D/Sears method. In construction, we have taken a glass tank filled with a liquid, a quartz crystal, a piezoelectric crystal, and we have also taken a sodium light as a monochromatic source of light, and a spectrometer and an RF oscillator. Coming to the working of the D/Sears method, initially the crystal is set free and monochromatic source of light is switched on. When this light passes through the liquid, we can see only a single image. I mean, no diffraction pattern is observed. Now, the quartz crystal is set into vibrations by giving the input frequency from the RF oscillator. Now, when the natural frequency of the quartz crystal matches the frequency of the applied voltage, then due to resonance, due to inverse piezoelectric effect at resonance, ultrasonic waves are produced. These ultrasonic waves travel through the liquid, they get reflected back from the walls of the glass tank, and they form a longitudinal stationary wave pattern with nodes and antinodes. The density of the liquid is high at the nodes and it is low at the antinodes. Therefore, the liquid behaves like a grating called as a acoustical grating. The principle of our experiment is that when ultrasonic waves travel through the liquid, due to the alternate compressions and refractions, longitudinal stationary wave pattern is formed with nodes and antinodes. Here, the nodes act as an opaque medium to the ordinary light and antinodes act as a transparent medium to the ordinary light. Thereby, we can see that liquid is acting as a grating called as acoustical grating. Now, when the monochromatic source of light is switched on, which is perpendicular to the direction of these waves, we get a diffraction pattern with central maxima and principal maxima on either side of it, and it can be observed in a telescope. Over to Dirishmini.
These are the diffraction patterns of various liquids what you observe. After the spectrometer readings, we got the determination of the parameters as wave parameters and acoustical parameters. Wave parameters are velocity, wavelength and frequency, and acoustical parameters are bulk modulus, adiabatic compressibility and acoustical impedance. From the above information, we got the results of the above data of the various parameters. And this is the final table which says about the comparative studies of the various ultrasonic wave parameters of different liquids. Over to Krishna Bharati.
Good evening, everyone. So, from the derived data, we plotted a few graphs of different parameters with respect to frequency. This is the graph of velocity with respect to frequency, and this one is that of wavelength with respect to frequency. Here we can see that as frequency is increasing, velocity is also increasing. And in the case of wavelength, as frequency is increasing, the wavelength is decreasing. Yeah, this is the graph of bulk modulus with respect to frequency. Bulk modulus is a property which helps us measure how resistant a substance is to compression. So here we can see that as frequency is increasing, bulk modulus, this is the graph of bulk modulus and frequency. Now this is that of adiabatic compressibility and frequency. Adiabatic compressibility is nothing but the reciprocal of bulk modulus. And this is the acoustic impedance. Acoustic impedance is the resistance that is given by the liquid when a sound wave is propagated through it. So this is the graph. Yeah, from the graphs and the derived data, we have observed that as frequency is increasing, the velocity is increasing, the wavelength is decreasing, and the bulk modulus is increasing. So bulk modulus is also related to velocity. For higher velocities, bulk modulus is more when the velocity is more. And we can see that as velocity is more, adiabatic compressibility is less. Since bulk modulus and adiabatic compressibility are inversely proportional, and bulk modulus and velocity is directly proportional to bulk modulus, we can see that in less compressible liquids, velocity is more, and in highly compressible liquids, velocity is less. And conclusions we have successfully performed this experiment using Debye-Sears method and using acoustic grating method. We have determined the wave parameters for ultrasonic waves from frequencies 3.5 to 4.5, 3.5 hertz, 4 hertz, and 4.5 hertz. These are the wave parameters we have determined. And we have observed that these wave parameters are changing with respect to the chemical constitution and temperature. So far, we have done this experiment for only one temperature, that is 26.5 degrees, which is the room temperature. And further, we will try to do this for more temperatures and more liquids. So far, we have done this for water and some organic liquids such as ethanol, methanol, and acetone. And we will try to do it for aromatic liquids also. These are the references we took our sources from. Yes, we are really grateful to our principal ma'am and our whole department of physics. Yes, thank you.
I think they have done a good presentation. Now this topic is open for discussion and a few questions from staff 2 and students 2. Anybody? Yes.
Can you tell me why you use a monochromatic source of light? You were talking about that. You know, many times you mentioned.
Yeah, ma'am. If we have used white light, it would have wavelengths ranging from 4,000 to 7,000 nanometers, angstroms. And we are not aware of any formula to receive the wavelengths. See, using this method, we can find the wavelength of the sound wave.
I know, but will it, the velocity, will it depend on the frequency or some such things? Or,
yes, ma'am.
On this frequency?
Yeah, we have seen that as frequency is increasing, velocity of the sound wave in those particular liquids is also increasing.
Is it?
Yeah.
Okay, let me see. Yeah. Okay.
That equation you check.
Okay.
Any other question?
So we have a formula V is equals to lambda F.
That is what I wanted to ask. Show that formula. That is without equation physics
V is
people-
equals to lambda f as velocity is increasing, frequency is increasing. That we have proved
Yeah,
using
sure,
this experiment.
Okay, here is one question regarding the defects.
Defects?
Okay, okay, okay.
Okay. When you pass ultrasonic waves through a defective solid, you observe reflection, no? Could you please tell a little more about that? Why there is reflection?
Because there is change in medium.
That is the point. That's right. Whenever there is a change of media, always the waves traveling in the media suffers reflection. That's good. You know about it. Good.
Yes, not only that, purity is also plays important role. What about other question? Because I won't ask question. Any of students? No, it is easy, you know. Yes.
It was a simple question. So in all your graphs, most of the you had 4 fluids. I don't remember which ones, but the ethanol graph always looked different from the others. So why did that happen, or is it just within experimental error, or is it something that is special about ethanol? If you could go back on a few more slides.
Go back, graph.
No, your results. Your results, yeah. So, ahead. Next. The
Next,
graphs.
graph. Different, yes.
This one. You see that most of them follow similar patterns. For example, for the first graph, the Bulls modulus, they don't change much, except for ethanol, which increases a lot. Again, for whatever the second parameter is, I can't see it from here.
It is adiabatic compressibility.
Right. So again, in that, it's very similar for most, except for ethanol, which there's a fall. And again, in the third one, there's a sudden rise over there.
Yes,
so that either shows that something is different about ethanol compared to the other 3, or there is just experimental error, which is possible.
Yes.
So, do you know why that has happened?
No, we'll try to find it out, sir.
Yeah,
Thank
anyhow, government of India by 2030, and they are producing more than 25% of ethanol. Because of that, all sugar factories working, and all farmers are getting happy, and I am also happy. I am sugarcane grower. Why? Because ethanol is a biofuel. Just to put a biofuel, will get all the properties. And also shooting is there at a particular frequency. Ethanol is having a special property of the susceptibility, and not only susceptibility, this your shear modulus. For that, what you have to do, being a physics student, you should have written that equation, C11 plus C21, that all you have studied in solid state physics, no? That otherwise, Ali Umar, you open that, you get that equation, you find out the shear modulus just by theoretical calculation. Or else some problems are solved, just you take it from that. Yes, any other question? Yes. Thank you very much for giving a good, but you can write this paper like a biofuel, because government is also giving funding. If you write the proposal to KSST, I am one of the chairman from Kalyana, Karnataka. Just, no? Hyderabad also Telangana, no? We are Gulbarga and Telangana is same. You write, just you come and sit in this Bidar border, you send a project. Yes, because all backward area, Telangana, Kalburgi, ultimately students should get benefit. Thank you.
Thank you.
Give a big hand. The next is 11. That is the Yukti R. Aishwarya S.V. Madhur K.R. Department of Mathematics, the National College, Jayanagar. Good. At least applied physics we are getting. Thank you. Anybody is there along with you? You want that height? Yes, you can use that.
it starts. Good evening, everybody. Myself, Yuktiyar from the Department of PG Mathematics, National College, Jayanagar. I'm here to present my project, Heat Transfer Analysis of Moving Straight Fin under the influence of magnetic field and radiation, under the guidance of Dr. K.R. Madura. Actually, basically, when the word fins, when we hear the word fins, everybody thinks of fish fins. But here we actually use in the industries also, but not the fish fins. It is a material which is used to transfer heat. So fins are generally extended surfaces to enhance the rate of heat transfer between a hot surface and its surroundings. These advantages of fins are it is an easy and cheap way to cool an equipment and to enhance increase the rate of heat transfer. Disadvantage is by the insertion of this fin, the weight of the weight of the equipment increases. This is the disadvantage of advantages of fin. So next, coming to the mathematical formulation, here we have considered conductive radiative straight moving fin with a rectangular cross section of the length B, thickness T and width W. The fins base temperature and environmental temperature are maintained respectively at TB and T infinity. The uniform magnetic field is applied along y direction in the absence of electric field. From the above assumptions, the governing equation is given by equation number 1, where Jc is equal to sigma into E plus V cross B is the current conduction current density. The energy flux vector of combined conduction and radiation is obtained by the base of the fin, which is given by equation number 2. By Fourier's conduction law, we can find Q conduction, that is which is given. So by Fourier's conduction law, the Q conduction is given by equation number 3, and using Rosland approximation, the Q radiation is given by equation number 4. Using equation 3 and 4 in equation 1, we get equation number 5, but Jc cross Jc by sigma is sigma into B naught square U square. The temperature variation within the flow is assumed to be very small in some conditions. Then the term T power 4 can be represented as equation number 7. Equation 6 and 7 using in 5, we get equation 8, which is in the dimensional form. Yeah, here the fin tip is insulated and does not conduct heat. So the boundary conditions can be given as follows. Then to non-dimensionalize equation number 8, we can consider non-dimensional quantities, theta and x, where theta is the non-dimensional temperature and x is the non-dimensional length. Then using the above non-dimensional quantities, we in equation 8, we get equation 9, where we get, after simplification, we get 4 non-dimensional parameters, that is R radiation parameter, M square is geometric parameter, H is Hartmann number, and P is the Peclet number. The non-dimensional boundary conditions are given by equation 10. So for simplification purpose, here we consider A is equal to P by 1 plus 4R and B is equal to M square plus H by 1 plus 4R. So using these in equation, so in 9, we get equation 12, which is a simple linear homogeneous equation. After applying non-dimensional boundary conditions, we get equation 13. We can also find rate of heat transfer from the base of the fin, which is given as follows, which can be found out using the formula for equation 14. After simplification, we get equation 16 as result. So next, here is the graphical representation for the 4 different parameters. First one is graphical representation for the variation of temperature distribution for different values of radiation parameter. Here, as we can see in the graphic, from the graphical representation, as the values of R increases, the temperature is also increases. Thus, the R plays an important role in the process of cooling an equipment. Next is the radiation, graphical representation for the variation of the temperature distribution for different values of geometric parameter. Here also we can see, in this graphical representation we can see as the values of M increases, temperature is monotonically decreasing. So because the values of M increases, as the rate of heat transfer is increased, as it is noted that the temperature and temperature increases as values of M, as values of M increases, temperature is decreased. Here, as it is noted that as it is noted that the strength of the magnetic field, more convective heat transfer through the fin, there is more conduction, there is more heat transfer through fin by conduction also, and resulting in enhancement of temperature distribution in the fin, and also consequently the rate of heat transfer is also increased. Next comes the variation of temperature distribution for different values of Hartmann number. Here also temperature is inversely proportional to Hartmann number. The values of here as the values of H increases, the temperature is also decreasing, which leads to the strengthening of magnetic field on the magnetic field effect on the system, and which leads to the decrease in the mechanism of convective heat transfer, and in turn leads to the increase in the increase in the yes sir, sorry, increase also increase in the conduction also. Here due to the existence of magnetic field, the effect of buoyancy force also magnifies, and fin convects more heat. Next comes the temperature distribution of different values of Peclet number. Peclet number is a non-dimensional number, non-dimensional speed, and it is defined as the advective heat to the diffusive heat. As the values of Peclet number increases, the temperature is also increased. Next, here we have considered 3 different materials of the fins. One is copper, silver, and aluminum. Graphical representation tells us that material used of the fin material which is used is copper, has more which conducts more heat. So this is because copper has more thermal conductivity. So results, they show that the moving fin profile plays a vital role in the temperature distribution, especially near the fin tip. As the fin moves faster, it is observed that there is cooling in an equipment. And from the graphical representation, we can conclude that radiation parameter and Peclet number is directly proportional to temperature. Geometric parameter and Hartmann number are inversely proportional to temperature. Higher values of thermal conductivity of different materials results in increase in the temperature. It can also be concluded that one can choose the different material of the fin as per the requirement of the industries. These are some of the nomenclature we have used in our project. Thank you.
Good mathematical equation. Graph, everything they have covered. And now it is open for discussion. Few questions from judges, later students you can ask.
Actual experimental result.
Sorry, sir.
Is there any experimental values of air? Have you observed experimentally or just
No, sir, we have referred some of the standard papers
Oh.
and took the values.
Could you give some values regarding the geometry of fin?
As in?
Geometry. You have used
Parameter.
geometrical parameters. You mentioned that, no?
Geometric parameters.
Yeah, whatever that might be. In the equation you used to refer, the geometry is one parameter. What exactly you mean by geometry?
No, sir. Actually, what we use M, what is that? We call it as geometric parameter.
I request Nagaraj to highlight that because you are in the same field.
Yes, non-dimensional.
Non-dimensional number means, like, sir, for example, I just tell you the other analogy. Something like a flat plate is, we are heating it, and above that the air is flowing. The temperature of the air may be about, say, 500 degrees Celsius. The temperature of the hot plate may be about 1000 degrees Celsius. We may write some theta. Theta is equal to T infinity by TW. T infinity means free-steam temperature. TW means wall temperature. Instead of conducting the experiment as such, we take that T infinity by TW is, let us say, half, 0.5. So we just give 0.5, 0.25 like that. The experimentalist can find out what would be the result by these values. So they have done only theoretical calculations. And what she said, some standard reference papers they have taken for experimental verification. But they have not done any experiment, but only the experimental data has been used. What would be the value for M, she said. That M she didn't define correctly. What is the value of M you have taken?
0.5, 1.
Yeah, like that, sir. This is what normally in mathematics department they are doing. But in mechanical engineering, they are doing experiment, actually heating and then allowing the air to flow. In mechanical engineering, they are doing. But here, they are used in vehicles.
Automobile.
Automobiles.
No,
So this is what
anyhow, just one suggestion I can put, because you are a theoretician, I can understand, but by the by, you have to keep in your mind, if you are working on this is thermal conduction and all these things, always some harmonicity, some equations are there, standard equations from first principle, use that. Another thing is, nowadays people are not talking about only bulk one, thin film, because once you go, the size of the thickness goes on, decreases, that will define one thing, aspect ratio. If aspect ratio changes, many property changes, that you look into that. Many papers are there, especially Bengaluru is famous for fluid dynamics. Rudra has 200 research paper, 200 PhD students they have done on their fluid dynamics. Lot of things is available. That is one thing. You look about the thin film and all these things. About the not only heat conduction is important. Nowadays, everything, 80% of electronics gadgets are using in automobile. Don't think only mechanical engineers are required. They require physics people, they require chemist people, they require electronic engineers. That means you have to do the work on thermal expansion, back calculation. Because for example, one of my students played an important role just by using the simple equation. What morning Krishnamurti was there, always he used to talk about the first principle and all these things and harmonicity, and they have calculated the thermal expansion. Luckily, what material we have prepared, glass and glass ceramic, that thermal expansion is matches to the thermal expansion of the metal, that is copper and steel. Therefore, lot of glass ceramic to metal sealing, lot of patent and all these things. Better you can, anyhow here, Nagaraj sir is there, he is expert in fluid dynamics and other people, and you can talk to Venkatesh sir. He give the hint, many things, just principle he will give. Remaining thing you have to follow, big gants are here, Somsekhar and all these things. They give ideas. Just you do all the thermal expansion, the conductivity and all these things. Okay. Thank you very much. Once again, if you have any question, last one question. No. Give a big hand to that theoretician because she is from mathematics. Thank you very much.
Thank you.
Next is OP12. Beneath Paricha. Yes. Whether it is loaded? 1 minute will tell you about your affiliation and all this.
The slides have been loaded.
ಅಣ್ಣ ಅಲ್ಲಿ ಸ್ಲೈಡ್ ಶೋ ಹಾಕಬೇಕು
ನಾನು ಬರ್ತಾ
ಇವಾಗ ಅವ್ರು ಸ್ಟಾರ್ಟ್ ಆಗಿದೆ
ಯಾವುದ್ರಲ್ಲಿ ಇದು
ಇವಾಗ ಅವಿನೀತ್ ಅಂತ ಸ್ಟಾರ್ಟ್ ಆಗಿದೆ
ಆನಲ್ಲಿ ಇರಲಿ ಅಲ್ವಾ
ಹಾಂ ಹಾಕ್ಬಿಟ್ಟು ಬನ್ನಿ ಫೋಟೋ ಸರ್
You are left or you are standing here? ಈ ಮೈಕ್ ತಂದಿದ್ದ ಈ ಮೈಕ್ ಬೇಕಿತ್ತಂತೆ
ಹೌದಾ ಹಾಂ ಸರಿ ಓಕೆ
ಲ್ಯಾಪ್ಟಾಪ್
Who is the next person? 13? Be ready.
Hello. Am I audible? Hello. Is it audible? Hello. Okay. Okay. So good evening, everyone. I am Abhineet Paricha, a 5th year BSMS student from IISA Mohali. My thesis guide is Dr. Shivke Sethi from RRI Bangalore, and I'm going to talk about WIMP decay as a possible warm dark matter model. First, I'll introduce you to the dark matter theory under the standard lambda CDM model, and I'll highlight its drawbacks. Okay, so what qualifies as a dark matter candidate? First, the dark matter should be able to explain the invisible density fraction that we have in our universe today, which is about 0.25. You can compare it to the baryon fraction, the visible fraction, which is only 0.05. So dark matter, the invisible part dominates the visible baryonic part in the ratio 5:1. So dark matter forms the dominant component of the universe's mass. That's why we expect it to be non-relativistic by matter radiation equality. The evolution of the universe, you can divide it into 3 phases: radiation dominated era, matter dominated era, and dark energy dominated era. Since radiation cannot cluster and form structures, the dark matter is what forms these galaxies, planets and all. It forms the potential wells where these structures form in the matter dominated era. That's why we want it to be non-relativistic. Finally, the dark matter should show gravitational interaction. It is massive, and of course it should not show any electromagnetic interaction because it is invisible. Okay. Next we move on to weakly interacting massive particles. What are these? Supersymmetry, an extension of standard model, predicts really massive particles of giga electron volt order that interact only weakly. So these particles, they show gravitational interaction, no electromagnetic interaction, but they show weak interaction, and they are non-relativistic all throughout. So the only thing that we now need to check is whether the relic abundance of these weakly interacting massive particles explains the density constraint of 0.25 for dark matter. So for that, we propose a self-annihilation mechanism. 2 WIMP particles annihilate to give off radiation. So in this way, it is coupled with the early hot plasma through this reaction. As the temperature decreases, this reaction cannot be maintained, because of which the WIMPs start decoupling and their relic abundance freezes out. This is the numerical solution for the quantum Boltzmann equation pertaining to this self-annihilation mechanism. This solution is characterized by only two parameters. One, the cross section, and the other, mass of the WIMP particle. For the cross section, we can vary the cross section, and we can see that lower the cross section, lower the annihilation, and hence greater the relic abundance. From that, we apply this density constraint and calculate the fit parameters. So the parameters that we obtain is 100 GeV mass for the WIMP particle, and the cross section is about 10 to the power minus 38, which is indeed in the weak interaction limit. So on one hand, we have a cosmological theory that requires us to have a particle of this mass, this cross section. On the other hand, we have an independent theory that predicts that, okay, there exists such a particle of this mass and this cross section. So this is what we call the WIMP miracle, and that places weakly interacting massive particles as the most favored candidate for dark matter and the lambda CDM model. But what are its drawbacks? First is the experimental detection. There was significant focus on direct detection experiments, which was basically WIMP and nucleon scattering experiments. However, they haven't been able to produce any detection yet. Though they have been able to at least obtain an upper limit on the WIMP nucleon scattering cross section. This is the results from the Xenon 10 collaboration paper. But you will observe that this 10 to the power minus 47 figure, it differs by 9 orders of magnitude from the theoretical relic abundance calculation which we just did. So this is the second drawback. Third, there are structure formation discrepancies related to the cold dark matter, cuspy halo, high fraction of thin disk galaxies, small scale crisis, filaments, small supermassive black holes. The reason for these drawbacks is the non-relativistic nature of WIMP itself, because of which it leads to only bottom of structure formation, like smaller structures form first, they merge together to give larger structures, and excessive structure formation at small scales. So these drawbacks are what motivated us to consider a warm dark matter model. So I will here formulate the new perturbation theory for the warm dark matter model, and I will show you the results by comparing it with the WIMP. Okay. So how does warm dark matter actually differ from the cold dark matter? The answer is in its mass. The mass of cold dark matter, WIMP, it was about GeV, whereas this is about kilo electron volt. Cold dark matter is, of course, less temperature, less momentum, it is non-relativistic throughout. But warm dark matter, it is initially relativistic, the co-moving momentum part dominates, but later on turns non-relativistic. Cold dark matter shows only bottom-up structure formation, whereas warm dark matter shows both bottom-up and top-down structure formation. Okay, so this is the same relic abundance calculation. The orange one corresponds to the WIMP one which we did earlier. I want you to consider another WIMP particle which has a lower cross section, 10 to the power minus 46, which is closer to the experimental upper limit. Since it has a lower cross section, it will have a correspondingly higher relic abundance, but we still want to maintain the same density constraint. That will require us to have a lower mass of dark matter particle. But now, how do we go from a heavier GeV mass WIMP particle to a lower mass dark matter particle? The answer is decay. We hypothesize that the heavy WIMP particle decays into a lighter dark matter particle, giving off radiation. For this decay, we assume that the WIMP particle has negligible momentum and that the mass of the dark matter particle produced is much less than that of the WIMP particle. So that will tell you, the relativistic kinematics will tell you that the momentum of the dark matter particle will be half the mass of the WIMP particle. So this and the fact that the numbers should be conserved during the decay, that will give you this background phase space distribution. The decay is characterized by two additional parameters, the epoch of decay, at what time it decayed, and of course the mass of the lighter dark matter particle. So this increases the parameter space that we had. Then we apply constraints to these four parameters. First, of course, the warm dark matter particle should turn sufficiently non-relativistic by matter radiation equality. This is the momentum of the warm dark matter particle, and this is the threshold momentum which we place at matter radiation equality. Rearrange the terms, you will get this equation. This is basically the ratio of mass and momentum of the warm dark matter particle, which you define as R. Next, it should satisfy the density constraint of 0.25. You will see that for the warm dark matter, this additional term has been introduced. And finally, the decay should occur after the freeze out. Okay, and this is the perturbation theory which I have myself formulated for the warm dark matter. These are the background quantities, first order quantities, and Boltzmann equations. The only take home message I need you to consider is that all of these equations depend only on the single parameter R. There are no other parameters to constrain them. And in the R tending to infinity limit, which basically means that the mass of the warm dark matter particle is being increased, it becomes more and more cold dark matter-like. Even these equations boil down to that of cold dark matter exactly. For R tending to 0 limit, the mass is being decreased, so it turns more and more massless neutrino-like, which is also reflected in the equations. Now, this is the numerical solution to the equations which I mentioned earlier. These are my own plots. The dashed lines correspond to that of cold dark matter, whereas the colored lines correspond to the warm dark matter models for differing values of R. On the y-axis, we have the density perturbation. How do we define it? We introduce first order perturbations to the background density, and we take its Fourier amplitude. So the Fourier amplitude has been plotted. Greater this, greater the structure formation. Greater the structure formation and greater the value. For lower values of R, the structuring decreases, which you can see in the characteristic oscillations. We can also see that in the same matter power spectrum. Matter power spectrum basically tells you how much each Fourier mode contributes to the total structure formation. So on this part, you can see that for lower values of R, the power spectrum indeed gets suppressed. So on the smaller scales, warm dark matter can actually suppress the structure formation and overcome the drawbacks of cold dark matter. So finally, testing against the Planck CMB data. This is the 2018 CMB temperature correlation which I have used. This is the angular power spectrum. The main effect of changing the value of R is increasing the enhancement of the first peak, which is due to increased ISW effect due to the increased radiation component from warm dark matter. These are the MCMC contour plots. The 2D confidence intervals tell us that the R parameter has been constrained up to a lower bound at about 2.7 to the into 10 to the power 5. With this upper limit and the 3 constraints which I had mentioned earlier, we can constrain the mass and cross section of the warm dark matter particle. You can see that the cross section actually turns out to be 10 to the power minus 46, which is much closer to the experimental upper limit. And the mass turns out in the order keV. So this tells us that we need to focus our direct detection experiments to keV mass particles instead of giga electron volt mass particles. And finally, in conclusion, a brief summary. The warm dark matter particle, it increases the parameter space, more space to explore. The model for the lower bound which I calculated indeed shows that the power spectrum is suppressed. The self-annihilation cross section which we calculated is closer to the experimental upper limit and hence more agreeable than the cold dark matter. The warm dark matter particle suggests that we need to focus our detection experiments elsewhere. Future work, the decay radiation could be explored as another cosmological observable, and the decay physics could be explored independently, not cosmologically, to remove the degeneracy on AD. We could include more data sets, of course, and we could require more small scale and high redshift data, which we expect from JWST. Finally, I'll leave you all with a quote. If only 5% of our universe has such rich physics to offer in forms of baryons in standard model, imagine the treasure hidden in the rest 95% in form of dark matter and dark energy. Thank you. These are my acknowledgements. Chief Supervisor, Co-Supervisor, and IAPT. References. Yes, sir.
First, judges, you can ask.
About the Boltzmann equations.
Yes, sir.
Surely Boltzmann hadn't worked upon this.
Yes, sir.
Boltzmann in his time, there was no such thing as dark matter.
Yes, sir.
But you mentioned Boltzmann equations. What exactly you mean by that?
Sir, I am saying that the Boltzmann equations are there. I introduced the first order perturbation theory to it.
Then my suggestion is that you call it as applied Boltzmann equation. Something
okay,
like
okay, sir. Yes, sir. Yes, sir.
Tag
sure.
to it, okay?
Yeah. Good. So it will be first order applied Boltzmann equation.
No,
yes, sir.
This is the senior suggestion.
Yes.
Students. Yes, ನಿದ್ದೆ ಹೋಗ್ತದ ಕ್ವಶನ್ ಕೇಳಿದ್ರೆ ಯು ಹ್ಯಾವ್ ಟು ಆಸ್ಕ್ ಕ್ವಶನ್ ನೋ ಡಾರ್ಕ್ ಮ್ಯಾಟ್ರದಾಗ ಏನು ಕೇಳ್ಬೋದು ಅಂತ ದೇ ಶುಡ್ ಆಸ್ಕ್ ಎನಿಥಿಂಗ್ ಡಾರ್ಕ್ ಮ್ಯಾಟರ್ 95%. ಎನಿಬಡಿ ಸೋಮಶೇಖರ್ ಸರ್ ಓಕೆ ಎನಿಯೋ ಗುಡ್ mathematical equation, but
yes, sir. So there are 3 types of experiments being done. One I showed you, the direct detection experiment, which is WIMP nucleon scattering experiments. Another is indirect detection. So what basically happens is that when dark matter annihilates, it gives off radiation. So what they're trying to do is they're looking at spheroidal galaxies where there is abundance of dark matter. So they expect that these dark matters will annihilate and give off radiation. So indeed, it has been observed by Fermi-Lat that an excess of gamma ray flux has been observed from some spheroidal galaxies, but not all. So that modeling is still undergoing. Also, there is collider experiments in LHC. So proton-proton collisions are done. Whatever part goes into the invisible spectrum, they are trying to detect dark matter in that sector. So these are the current updates of the experimental part.
Any question from student side? Anybody? No. I will ask one question. Just simple question.
Okay, sir.
Because you plotted a graph very beautifully out
Yes,
done.
sir.
I think all these are simulated. Or Monte Carlo.
Data analysis and my own code
yes,
work.
I can
Yes,
guess this. But you mentioned there, because already professor has mentioned that equation is that applied something they have to put.
Yes, sir. These are the perturbative equations.
Now, whether somewhere I saw that equation k minus k dot being a physics teacher, Kronecker delta or something else that is.
Okay.
Yes.
Okay, I can show you. That is the like important
because
part. This is the delta, right?
That delta and again in somewhere
Yes,
delta
sir. So
k minus k dash.
that is a power spectrum, sir.
Power spectrum,
Later on,
yes,
it
yes,
was a bit earlier. Okay, but this delta is due to the fact that we have assumed the heavier dark matter particle has negligible momentum. Once it decays, it imparts half of its energy to the
Now,
lighter dark matter particle.
you see your equation, equilibrium and non-equilibrium.
Yes, sir.
That
So
equilibrium
yeah,
is
this is the
around
quantum Boltzmann equation.
1.7 or somewhere it reaches.
Yes, sir.
And also density comes out to be 0.25. Again, it changes drastically.
No, sir, the 0.25 is due to the relic abundance.
Relic.
Yes, sir.
And what about that?
This was it moves out of equilibrium, sir. The reaction as the
No,
temperature
you have
goes
put
down.
for that equilibrium.
This is only for to show you that up till this part it was in equilibrium with the expansion.
And then this is extrapolation. Extrapolation.
This is extrapolation. This is the extrapolation part.
It is
not the real one. If it had been in equilibrium, then it would have followed this. But since it is not in equilibrium, it freezes out.
No, it is more or less, it is exponential decay is there.
Yes, sir. Yes.
E raised to minus x.
Yeah.
You can put anything that follows that equation.
Yeah.
No, I thought that somewhere it is a Kronecker delta is there.
Kronecker delta. Okay. It was
if it is Kronecker delta, lot of things because you use the psi function and all these things. Somewhere I saw. Anyhow, I can discuss with you. Yes. What is
it? Okay, so this is how the power spectrum is defined. It's a two-point correlation function. So if I take k is equal to k dash, then it will basically become magnitude square of the Fourier amplitude. So this will tell you what is the probability of a galaxy forming at that point in space.
Because you are using the Fourier transform.
Yeah. That's why it comes around. Yeah.
And you can use the Monte Carlo. No, you can get the fitting becomes very good.
Yes, so that's what I did. I used Monte Carlo.
No, that's not used the Monte Carlo.
So after this I took the linear matter power spectrum, converted it into the angular power spectrum, and then did the Monte Carlo matching with the original Planck data, which I showed you in this one. So that linear power spectrum I converted into angular one, then did the MCMC thing and got these results.
No, because if it is a Monte Carlo,
Yes,
the
sir.
decay tail should be entirely different.
Decay tail?
Mathematically.
Okay.
Because once you do the all data
No, sir,
into
the linear power spectrum is
all
not-
data into Fourier transform and then use the Monte Carlo, and you will get that graph something
no,
is
sir,
different.
the
Anyway, I will
linear
discuss
matter
with you.
power spectrum.
Yes,
Okay.
yes. This is out of your case. Thank you once again. You give a big hand. And what about the OP 13? 13 is not there. Who is that 13? They allotted 13. S. Shilpa, G. N. Anil Kumar, Siddhalingeshwar BP, N. Shivshankar Reddy, A. Jayasheela, the Presidency University, Bengaluru. Anyone out of these, if anyone is there, you can present the things. Not there? Volunteer, please look. If it is not there, one more paper allotted in this session is oral presentation 5. Who were absent in the morning? Yes, you can. And ask judges to include that. Oral presentation 5. Kokila Madam was their chairman earlier, and I think somehow it is missed.
मेल में आदित्य शेखर roaming around or staying here?
So the pointer is this one.
This is next.
Yes.
This is previous.
Yes.
This is pointer.
Okay.
Good. Good luck.
Thank you. Very good afternoon to everyone. This is Aditya Shekhar from NIT Raulkela, and here I am to present my presentation of Nasikon structured solid state electrolytes for all solid state devices and application. So first of all, what are the batteries? Batteries are the most important and the devices that are being used by us in our daily lives. Imagine a world where there is no batteries. All the devices will be connected to a plug point or something. They will not be portable to anyone. So will it help us? Absolutely no. So batteries are, the single unit of the batteries are known as shells, and batteries are just a device which converts the chemical energy into electrical energy. The principle that is mostly used in the batteries are the redox reaction or electrochemical redox reaction. So this is the working principle of a simple battery in which two electrodes are present, cathodes and anodes, in which one of the electrodes, which is known as anode, undergoes the oxidation, and the other one, cathode, undergoes the reduction. In the most basic working principle, that implies in one of the electrodes, electrons get sufficiently loaded due to the chemical reaction with the electrolyte, and the electrons flow from the higher potential to the lower potential. So the batteries that are being used have some of the limitations, such as in the first figure we can see the lithium raw material supply in the whole world. The most of the batteries that we use are the lithium ion batteries or the lead acid batteries. As we can see, the materials that in the worldwide, 46% of the lithium is available in the Australia only. So the depleting, and the resources are day by day depleting. The next disadvantage is the liquid electrolytes that are being used in the batteries are mostly corrosive in nature, volatile, and sometimes they may be toxic, due to which in the leakages, during the time of the leakages, they will also harm the people who are using it. The liquid electrolytes are usually thermally unstable. What is the meaning of thermally unstable? Thermally unstable usually defines when the liquid electrolytes undergoes a self-sustaining reaction in which they undergoes recrystallization or polymerization such
type of techniques in which the batteries are of no use later on. The other are the leakage, flammability, and dendrite. What is the dendrite formation? At the time of the electrolysis or the redox reaction happens, so the cations get collected over the cathode, and due to the accumulation of it, they can come and touch to the anode, which leads to the short circuit. These are some of the images in which we can see the damages that this is the leakage problem, these are the flammabilities, this shows the dendrite formation, this also shows the leakage problem. Recently in news we came up with that most of the Ola who are delivering the electric powered vehicles, in which we can see that due to the use of liquid electrolyte only, the flammability occurs. So those are sent to the DRDO office for reporting the faults. And so to the solution of the liquid electrolytes, we come up with the solid state batteries, in which we mostly use as the solid state electrolytes instead of liquid electrolytes. So what is the basic difference between the normal batteries and all solid state batteries? The basic difference, we can already see that the electrolyte used in the conventional batteries are liquid, and the batteries we are introducing as solid state batteries using as a solid state electrolyte, solid electrolyte. So what are the advantages if we use the solid electrolytes? The advantages are like they are thermally more stable, there is no leakage, non-volatile, and decreases the chances of catching fire as well. Instead of used in the batteries, the solid state electrolytes are also being used as in the ionic devices like the gas sensors, fuel cells, and supercapacitors. Now comes what are the types of the solid electrolytes. One of the two most common categories are the organic and inorganic. The advantages, properties of the organic electrolytes are they are more flexible and easy contact. As there will be more easy contact, it will be more helpful for getting into adsorption and all, which helps us for getting the more proficiency from the battery. There are some of the disadvantages that we get in the organic electrolytes, like low melting points, and it easily catches fire. We can see that it easily catches fire at 50 degrees Celsius, so it's very hard to use in the room temperature and all. Next comes the inorganic electrolytes. They are mostly have a high temperature requirement and high contact resistance, but they were actually moisture reluctant, which is an advantage, as well as high voltage capacity and high grain conductivity. As we get a high grain conductivity, we get the more proficiency from the inorganic electrolytes. The examples of the inorganic electrolytes are like nasigon, garnet, antiperovskites, alumina composition compounds. The compound on which we were working was nasigon. So the nasigon preparation is as this. The chemicals that are used here are Na2CO3, ZrO, Cl2, SiO2, and NH4H2PO4 that we get as nasigon, as well as we get the byproducts as CO2 and NH4 as well. So this is the natural structure of the NZSP. You can see there are interstitial sites in between the structure. So how the conduction happens in this NZSP is that the more the Na ions that are being induced in the NZSP structure, they transfer from one place to the interstitial site, and they replace the other atom, and that atom goes to the other interstitial sites. This cycle goes on, and we get the conductivity through this. So this comes the preparation, how we have prepared the NZSP in our labs. So first we took the measuring of the compounds, and then we took the grinding with the agates measure. Then we put that powder for the calcination into the furnace for 700 degrees Celsius for 2 hours. Next goes for the sintering process, in which we put that sample to 100 degrees Celsius, 1000 degrees Celsius for 2 hours. Next come the pelletizing of the powder that we had been put into the pelletizer to make these forms as the pellets. Then they are put for the annealing, so that the pellets that are made should undergo the recrystallization and proper grain structure. Then we apply the silver paste over it for better conductivity over and put it into the sandwichometric characterization. So these are the processes in which we have used the chemicals used. We have measured the compounds with the agate smasher and others. We use the furnace and palletizers and all. These are the furnace, and this is the characterization technique that we have used. So here comes the characterization results. In the characterization results, we can see that there are two plots we have made. One was under the pressure of 1000 psi and next was under 500 psi. In 1000 psi, we can see a greater conductivity, which is mostly due to as applying more pressure, there will be less amount of gaps in between the samples. The activation energies of these two plots has been recorded as 0.49 electron volts, which is very near to the theoretical value, which was about 0.46 electron volts. As we can see, due to the proper densification of the NZSP sample prepared in 1000 psi, we get a better conductivity here. The most of the parameters that are being used are under 12.5 kilohertz and the voltage of frequency of 12.5 kilohertz and the voltage of 60 volts. So we have also presented a sample like undergoes the cycle of 3 to 4 times. Under this, the black one shows the cycle of cycle 1 and the purple one shows the cycle 4. We can see a slightly better conductivity in cycle 4. This can be due to the drying of the silver paste that we have applied previously. Now comes the characterization results of doping of NaI along with the NZSP. We can see that the highest ionic conductivity increase in the 6% and the 4% of the sample. The purple one shows the pure NZSP sample, and the blue one shows about the 4% and the green one shows about the 6%. We can see the roughly an order of 0.1 increase in conductivity as in 6% and 4%. So, I have more. Okay, sir. So in more than and in 8% and 6%, we can see that in the 8% there is a decrease in the conductivity of the samples, and the 10% and 8% are mostly near to the NZSP sample only. So here comes the comparison of the temperature of different ionic conductivity of pure NZSP and NaI content based. We can see that the most of the graphs shows the similar nature, but there is a increase in conductivity as we go increase in temperature. So here we can conclude that like if we get a higher temperature, we can get a better conductivity. So here comes under the XRD analysis and all, in which we can see that XRD analysis usually gives us a rough idea of the structure of the sample. So this shows the pure NZSP. This is 4% doping with NaI and 6% doping with NaI. In the figure, like the peaks around 2 theta equal to 20, 23, 27, 31 are in agreement that NZSP follows the structure of the monoclinic structure as well. But there are some additional peaks as well, like 22, 32 and 34 are suppressed as compared to the pure NZSP. And the additional peaks at 32 is due to the formation of NaCl, as we have used the raw compound of ZrOCl2 in place of ZrO6 or ZrO2. And there is no additional peaks associated with I- as we have used the doping as it is absorbed in the doping of NZSP sample. So these are the FESM images that we get from the samples. This is of 1000 psi of pure NZSP, and this is 500 psi of pure NZSP. It purely shows that there is the ingrain gap in 500 psis are more as compared to 1000 psi. And this is the NaI 4% doped of NZSP. Due to its glassy behavior of NaI, it shows increase in conductivity as compared to the pure NZSP. So I thank Mr. H.C. Verma, Professor H.C. Verma sir to provide us the platform and the whole Shiksha Sopan community. So provide us the platform to conduct these type of experiments and all. And our professor guide was Mr. Deena Chandra Singh, who was a postdoctoral fellow from IIT Kanpur as well. And I would also like to thank you IIT Kanpur Physics Department to provide us the access of XRD as well as FESM facilities. Thank you everyone.
Good. Courageous person. Physics is different, courageous person is different. I will request judges to ask question.
What happens to the size of the batteries, when you use solid state electrolytes? Will they become bulkier or?
No ma'am, it will be same structure.
Same size?
Yes.
They won't decrease actually?
It will also decrease, ma'am.
It will decrease,
Yes,
yeah, because that is what we are looking into,
Yes.
the sizes should be very small.
Yes, ma'am.
Thank you.
Any question from student side? Yes, you can ask.
Duty cycles. So can you tell how many duty cycles will solid state battery support?
As we have concluded the experiment, it shows a better duty as compared, like if lithium ion batteries goes to 5 to 10 cycles, it will go up to 20 cycles.
That's nice.
Yes, Judge.
In one of the slides you have mentioned about contact resistance. So what will happen if this is like a liquid electrolyte or if this is a solid electrolyte? How will you reduce the impact of contact resistance?
Like sir, contact resistance, if we use inorganic substances, the contact resistance increases, which helps for a better conductivity.
Is it helpful for better conductivity?
Yes sir. Because in solid electrolyte that we are using, it needs a better conductivity, better contact with the cathode and the anode. So it will help for the better conduction.
So higher contact resistance is favorable.
Sorry sir?
Higher contact resistance is favorable.
Yes sir.
Okay.
Yes. Any other question? Huh? Judges. Last, this is almost.
Really last.
And Professor Nagaraj is not worried. You can ask any question. I have trained, I have to rush.
Okay, sir. Last. See, you have studied an inorganic compound, but it has a component carbon CO3 in it, no?
Yes.
Now, tell that you have sintered the compound at 1000 degrees centigrade.
Sorry, sir, sorry.
You have sintered this compound at 1000 degrees centigrade, that too for 2 hours. So now, what will be the strength of this carbon-oxygen bond at that particular temperature? Will it not?
Sir, in the reaction I had showed like the carbon dioxide and the NH4 has been much left at the time of sintering only.
There was no impact.
Like at the time of calcination, sorry sir.
Okay.
First we have calcinated for 700 degrees Celsius.
Right.
And then we went for the sintering for 1000.
But yet it feels the
yes
temperature.
Sir, some of the compounds will also stay there.
Also,
yes sir.
No, they will not break up. They will not break up that compound. That compound doesn't decompose because at very high temperature.
No, sir, it didn't break. Yes sir.
It doesn't decompose.
No, sir, like we made the pellets.
Okay.
The pellet was didn't break over the characterization. Yes sir.
Okay then. Right, thank you.
Okay. Can I ask or not?
Yes sir. Sure.
Huh?
Yes, sure.
You take sportive. I am asking student, not guide. Huh? You see, being a glass scientist here, number one is he mentioned about the glass without showing any glass transition. That is the what can I say, you can understand. That is one graph you have shown, that is a glassy. That is one. You can rectify later. Yes. And he mentioned about this by heating and the ultimately glass scientist under Canada Kumbar iddanga now. First two things we'll do. First we'll mold and heat it, that is the one thing. Another thing, directly we'll heat and we grow the crystals, that is another thing. Two approaches, glassy approach and sintering approach. Anyway, he had done or not, I don't know. That is left to him and his guide. Because whenever any material is there, I think here all stones are there, if you heat, dissociation takes place.
we talk about the heat of fusion and all these things. Many of the element changes, that reaction is there. Before going for the sample, that dissociation reaction they have to write. I think they are not aware of anything. Either they are taken from anybody or just they have put that. That is a different story. Another thing, sorry, you take it sportively.
Yes.
I am talking to you, not to guide. Another thing he mentioned about the contact resistance. Contact resistance is not a simple, being a research student. If you talk about the contact resistance, many people high rated in IITs, IISc, those professors, they talk 6 monolayer, 3 monolayer by doing some experiment like that. It is not easy. If you want to do contact resistance, simple equation you do in the BSc. What is that? Impedance, admittance. If you connect in series, some equation you will get. If you connect in parallel, some equation you will get. They have to use that. If not, you refer my paper, Yoga, just you will get it. Contact. Sorry, I will complete. I have to rush to train is there. And another thing I will request everybody, write the significant figures. First you follow research ethics. And those scientists are, professor are, Rajkarani are, prime minister are. First you follow the research ethics. And that is the only courage you will get it to talk on the dais. Don't take data from anybody. You generated the data. You can say my data are 10% wrong. What is there? You have developed your indigenous. That you have to do it. Plot graph carefully. Whether it is a simulated graph, it is not difficult nowadays. All softwares are available. You see here, if you are rich enough, you go to the kaleidograph. If you are not rich, copy origin. Just you put X and Y graph, that gives the graph.
Same.
And all fitting that will give, least square fitting will do. Or you write your own equation, accordingly all data will get it. It is not difficult nowadays. Students, just you read all mathematical. You spend 2 months, that is statistical analysis book. Because we are old, we forget all the equation. We have our family. We are not helping students. All statistical analysis, wherever that course is there, you attend that, and you will be better than your guide. Now this is my request to everybody. You don't take seriously individually, and all things you follow. Once again, I am very thankful to Nagaraj, and all the way, 13-hour journey I have done, and being a farmer, there are more than 40 laborers are in my land. Now, because IAPT, because whatever that grow, myself, Samant, everybody, along with our teaching, we have grown with the IAPT. Therefore, that is the point I have come here. Thank you very much. Once again, I am thank you to the Nagaraj.
Hello. Let us thank Professor M.S. Jogad and give him a good applause. Thank you, sir. Sir Somshekar. Cultural program in the next auditorium, that is actually called HN Kalakshetra, the next building only. So you have to enjoy the cultural program now, and that cultural program is performed by our own students of national, College, Jayanagar, degree as well as postgraduate students. So please go there and enjoy the program. Thank you for the day. And after that, again, immediately after the cultural program, the dinner will be available here itself. Have your dinner and then you can adjourn for the day. So thank you for the time being.